Hello there, and welcome to the Cosmographer. Every object on tonight's list has forced a working scientist to put the word artificial into print. Not a tabloid writer. A scientist in a published journal with a reputation to lose. 10 real, named objects. One is a moon of Mars that one of the Soviet Union's greatest astrophysicists calculated, from its orbit alone, had to be hollow. One is a star 1,400 light-years away that switched off more than a fifth of its own light, without warning or pattern, in front of the one telescope capable of catching it. One is a pair of photographs from 1952 showing 3 star-like objects that vanished from the sky in under 50 minutes, 5 years before any nation on Earth could place a single object in orbit. And the object at number 1 did not stay in the sky at all. It came down over an ocean, and human beings went to the bottom of that ocean to look for what was left of it. The 10 are ranked by a single rule. How much of the question, was it built, remains open tonight. Get comfortable and settle in. If you are the kind of person who falls asleep best with one honestly open question for company, a quick like and subscribe helps this channel reach more curious minds like you. Because by the time we reach number 1, the question will stop being hypothetical. Let's begin at number 10. Number 10, the mystery object that really was artificial. This is a list of 10 real objects, and one honest question asked 10 times over. The question is simple to say and difficult to answer. Was it built? Every object on this list is real, catalogued, and named. Every one of them, at some point, moved a working scientist to put the word artificial into print. Not a tabloid writer, and not an anonymous voice on a forum. A scientist, in a published venue, with a reputation to lose. That is the entry fee for this list, and it is a high one. The sky is full of strange things, but very few of them have ever forced that particular word out of a careful person. The 10 objects are ranked by a single rule, and the rule is worth stating plainly, because it will carry us through the whole night. They are ordered by how much of the artificial question is still open. At the bottom of the list sit the cases that have been closed completely, where the question was asked, tested, and answered. In the middle sit the objects where the artificial reading was retired, but the object itself still refuses to explain where it came from. And at the top sit the open cases, the ones that are still inside the machinery of science right now, with no exit in sight. By the time we reach number 1, we will arrive at the only object in this entire category for which human beings may actually hold physical pieces, sealed in a laboratory, under argument at this very moment. We begin with a case that was solved, and we begin there on purpose. Because before you can take any of this seriously, you need to see that the question can be answered at all. You need to see the method work, start to finish, on a real object. Number 10 is that object. It appeared in our sky as a genuine mystery. It behaved in ways no asteroid should behave, and within 3 months, science identified it beyond any doubt. It was artificial. It simply was not theirs. On the 17th of September 2020, a survey telescope called Pan-STARRS-1, sitting on the summit of Haleakala on the island of Maui, detected a faint point of light creeping across the stars. Pan-STARRS is a workhorse. It photographs the sky night after night, and its software compares each image to the last, flagging anything that moves. Most of what it flags is ordinary, the routine gravel of the solar system going about its orbits. This object received the designation 2020 SO, and it was filed, at first, as a small, near-Earth asteroid of the Apollo class. That filing did not survive close inspection. The first thing wrong with it was the orbit. 2020 SO was circling the Sun on a path almost identical to Earth's own. It took about the same time to complete one circuit. Its path was nearly circular, where most small asteroids trace stretched ovals. It was barely tilted with respect to Earth's orbit at all. That combination is remarkably rare in nature, and there is a good reason why. An object sharing Earth's lane meets Earth again and again, and each meeting gives it a small gravitational shove. Over thousands of years, those shoves add up, and the object gets scattered onto a different path. Earth's lane, in other words, cleans itself. Anything found drifting in it has not been there long. So the question asked itself, if this object arrived in Earth's lane recently, where exactly did it arrive from? The second thing wrong with it was the speed. 2020 SO approached Earth at roughly 0.6 kilometers per second relative to our planet. For comparison, a typical near-Earth asteroid sweeps past at many kilometers per second, often more than 10 times faster. This object was drifting toward us gently, the way a boat drifts toward a dock. And that gentleness had a consequence. In November of 2020, Earth's gravity reached out and simply kept it. The object slipped inside what astronomers call the Hill sphere, the region of space, roughly 1.5 million kilometers across, where Earth's pull outweighs the Sun's. It became a temporary second moon of Earth. It was not the first object ever to do this. A small body called 2006 RH120, a few meters across and thoroughly natural, was captured the same way in 2006 and released about a year later. So a temporary moon, by itself, proves nothing. It is worth pausing on that earlier visitor for a moment, because it is the control case for this whole entry. 2006 RH120 was discovered by the Catalina Sky Survey in Arizona, and for a while it too was suspected of being a returned rocket stage, because the suspicion runs in both directions. Astronomers measured the pressure of sunlight on it, found the push far too weak for a hollow shell, and concluded it was solid rock, a genuine wandering boulder that our planet had borrowed for a year and then returned to the Sun. Nature, in other words, really does capture small moons from time to time, and science had already practiced telling the natural ones from the built ones. When 2020 SO arrived, the examination room was ready. And this new patient gave astronomers something precious. It gave them time and a close target, and they used both. Through the end of 2020, SO looped around our planet on wide, wandering arcs, entering and leaving through the weak gravitational gateways near the balance points of the Earth and Sun. And as trackers refined its path night after night, a third anomaly emerged, the one that broke the case open. The object was being pushed. Not by gravity. Gravity was fully accounted for. Something else was nudging it off course, steadily and gently, and the direction of the nudge pointed straight back at the Sun. The push was sunlight itself. Light carries momentum, and when it falls on any object, it presses on it, very faintly. For a solid 10-meter boulder, that pressure is so small compared to the boulder's mass that it barely registers. But 2020 SO was responding to sunlight roughly 10 times more strongly than a rock of its size should. The arithmetic of that is unforgiving. For sunlight to steer it that visibly, the object had to present a large surface while containing almost no mass. It had to be, in plain language, light for its size. A shell. Something wide and hollow and thin-walled. Nature makes very few things that are wide, hollow, and thin-walled. Engineers make them constantly. Keep that test in mind, by the way. The ratio of an object's area to its mass, read out through the pressure of sunlight, is one of the sharpest instruments in this entire video. It will return twice more tonight, on two objects far stranger than this one, and it will give a different answer each time. While the trackers measured the push, Paul Chodas was working the problem from the other end. Chodas directs the Center for Near-Earth Object Studies at NASA's Jet Propulsion Laboratory in California, and his specialty is the long arithmetic of orbits, running them forward and backward through time like film. He took the measured path of 2020 SO and rewound it. Back through the decades the object went, looping around the sun, drifting ahead of Earth and falling behind again. And in late 1966, the rewound film showed something that made the whole mystery collapse into history. The object passed so close to Earth, so slowly, that it did not look like a flyby at all. It looked like a departure. The object appeared to be leaving Earth. Chodas pulled the launch records for the autumn of 1966 and found exactly one candidate sitting in the window. On the 20th of September 1966, an Atlas Centaur rocket lifted off from Cape Canaveral carrying a spacecraft called Surveyor 2. The Surveyor program was America's series of robotic moon landers, the machines sent ahead of the Apollo astronauts to prove the ground would hold them. Surveyor 1 had landed beautifully in June of that year, returning thousands of photographs from a lunar plane. Surveyor 2 was meant to follow it down. It never got the chance. During the mid-course correction on the way to the moon, one of its three small steering thrusters refused to ignite. The spacecraft began to tumble. Controllers tried again and again to restart the stuck thruster, 39 times in all, and it refused 39 times. Surveyor 2 spun helplessly past its target and struck the moon near the crater Copernicus, a failure logged, mourned, and eventually filed away. The crash itself deserves one sentence of respect. The surveyors were not science fair projects. They were the advanced scouts of the Apollo program, sent to answer a question that sounds absurd now and was deadly serious then, which was whether the lunar surface would bear the weight of a landing craft at all, or swallow it in dust. Surveyor 1 had answered yes for one plane. Surveyor 2 died trying to answer it for a second, and 5 more surveyors would fly after it, so that when human beings finally stepped down onto that ground in 1969, they stepped where robots had already pressed footpads into the soil and measured how far it sank. But this story was never really about the lander. It was about the stage that threw it. The Centaur upper stage was, in its day, a quietly revolutionary machine, the first rocket stage ever flown on liquid hydrogen, the fuel that would later power humanity's largest launches. It was a stainless steel cylinder roughly 12 meters long and 3 meters wide, and its walls were so thin that the stage could not even support its own shape unless its tanks were kept pressurized, like a steel balloon. Having flung Surveyor 2 toward the moon, the spent Centaur coasted on, empty. It swept past the moon, and the moon's gravity ushered it out of the Earth's neighborhood entirely, into an independent orbit around the sun. And there it vanished from human attention. Not from space, only from attention. No telescope tracked it. No catalogue carried it. For 54 years, the abandoned stage circled the sun alone, crossing and recrossing Earth's path. Picture it there, in the long middle of that half-century. The cylinder is tumbling, slowly, end over end, its steel skin still bright on the sunward side and black with shadow on the other. The hydrogen frost of its last burn boiled away decades ago. There is no sound, no drag, no weather, nothing to age it but sunlight and the occasional kiss of a dust grain. It crosses Earth's orbit again and again, a silver length of 1960s engineering holding its line through the dark. On Earth, The engineers who welded its seams retire and grow old. The crater its lander made sits silent on the moon through 600 lunar days. Nobody is looking for it, because nobody imagines there is anything to find. It is not lost in any physical sense. Every second of those 54 years, it is exactly where gravity says it must be. It is simply unwatched. And then, on a September night in 2020, on the summit of a Hawaiian volcano, a telescope built by the grandchildren of its era photographs a faint moving light, and a piece of software flags it, and the long solitude ends. The identification still had to be proven, and the proof is the part worth remembering, because it shows what closed means. Vishnu Reddy, a planetary scientist at the University of Arizona's Lunar and Planetary Laboratory, led observations of 2020 SO using NASA's Infrared Telescope facility on Mauna Kea. In early December of 2020, the object made its closest approach to Earth, passing about 50,000 kilometers away, roughly 1/8 of the distance to the Moon, close enough for careful spectroscopy. When sunlight reflects off a surface, the surface leaves its fingerprints in the light, dimming some colors and returning others, and every material writes a different signature. Reddy's team spread the object's faint light into a spectrum and compared it against the known families of asteroids. It matched none of them. Then they compared it against something else, laboratory measurements of stainless steel, specifically the 301 alloy that Centaur stages were manufactured from. The match was close, but the team wanted the case airtight, and what they did next is one of the finest small moves in modern observational astronomy. They found another Centaur stage, one from a 1971 launch, still circling in a high Earth orbit where it has drifted for decades, and they pointed the same telescope at it. Same instrument, same technique, one object known beyond doubt, one object in question. The two spectra agreed. Weathered steel answering weathered steel, across half a century of exposure to the same sun. That is how the file closed. Not with an opinion, but with a chain. An impossible orbit traced backward to a launch date. A measured push from sunlight demanding a hollow shell. A spectrum matching a specific alloy from a specific assembly line in 1960s California. In March of 2021, 2020 SO drifted back out through the gravitational gateways it had entered by, escaped Earth's hold, and returned to its own patient orbit around the Sun, where it remains tonight, catalogued at last, its mystery spent. It will drift near Earth again in the decades ahead, as its orbit and ours breathe in and out of step, and when it does, the catalogues will greet it by name. There is even a quiet afterthought among space historians that a future mission might one day retrieve it, the way museums retrieve sunken ships, because it is now among the oldest intact pieces of the space age still sailing, older than almost anything in orbit around Earth itself. And yet number 10 leaves something behind that the rest of this list has to live with. For a few weeks in the autumn of 2020, before the traceback and the spectrum came in, astronomers were genuinely entertaining an object in Earth's sky whose behavior fit no natural category, and the honest answer to what is it was nobody knows. The resolution, when it came, was humbling in a very specific way. The first artificial mystery object modern astronomy ever caught in the act turned out to be a message from ourselves, a piece of our own early space age coming home after 54 years, wearing just enough strangeness to be mistaken, briefly, for something else. We have been fooled before, and it is worth saying exactly how. We have been fooled by ourselves. Remember that sentence? It is the standard of proof this whole list answers to, and when it returns at the very top of the countdown, at number 1, it will mean something considerably less comfortable than it means right now. Because here is what the solved case proves. Artificial is not a mood, and it is not a headline. It is a measurable property of an object, written in its orbit, its response to sunlight, and the fingerprint of its surface. Science asked the question of 2020 SO and got a complete answer in under 3 months because the object stayed close, moved slowly, and belonged to a catalogue we could check, our own launch history. Every object remaining on this list is missing at least one of those mercies. Some were too far away to test. Some were gone before the instruments could turn. Some sit in archives 70 years old, beyond the reach of any follow-up. And one, the last one, may be sitting in pieces under a microscope, while the argument about it burns on. The next object on this list was also called an alien satellite, and for far longer than 3 months. It has been photographed, published, and believed by millions. It took a century to assemble, and the strangest thing about it is this: it never existed at all. Number 9. The alien satellite assembled from a century of stories. The story goes like this. There is a dark object in orbit around the Earth, circling from pole to pole, and it has been there for 13,000 years. It is called the Black Knight. It watches us. Governments know about it and say nothing. It has been detected by radio pioneers, tracked by the military, seen by astronauts, and finally photographed in crisp detail, hanging black and angular above the blue curve of our planet. If you have spent any time at all in the darker corners of the internet, you have seen that photograph. Number 9 is on this list because the Black Knight is, in one sense, the most famous artificial mystery object in the sky. And it earns its low position on the countdown because the case is completely closed, in the most instructive way possible. The Black Knight is not one object that was explained. It is 5 or 6 separate events, spread across an entire century, that had nothing to do with one another, and were welded together after the fact into a single watcher. Every piece, examined on its own, has an explanation. The myth lives only in the welding. And before we climb into the genuinely open cases higher on this list, we owe ourselves a careful look at how such a thing gets built, because the Black Knight is the cautionary mirror this whole video will keep glancing into. This is what it looks like when the pattern-hungry human mind constructs an artificial object out of noise and longing. One more thing about the world these stories grew in. For almost all of the century in question, the sky was empty. Not empty of stars, but empty of us. Nothing human orbited the Earth. Not one bolt, not one scrap of foil. And so anything strange overhead had to be either natural or someone else's. Hold on to that phrase, an empty sky. It is the soil this myth grew from, and later tonight, at number 5, that same empty sky is going to stop being a comfort and become the single most unsettling fact in a genuinely unsolved case. The oldest layer of the Black Knight is Nikola Tesla. In 1899, Tesla was working at his experimental station in Colorado Springs, chasing his lifelong obsession with the wireless transmission of power and listening to the natural electricity of the Earth with receivers of his own design. That winter, he recorded something that stopped him. Rhythmic disturbances, orderly repetitions, signals that seemed to him too regular to be storm static. Tesla came to believe he might have intercepted an intelligent transmission, and he eventually suggested it had come from Mars. It is easy to smile at that from here, and it is fairer to remember what was known in 1899, which is that nobody knew the sky itself broadcasts. Radio astronomy would not be born for another 3 decades. Nobody on Earth knew that Jupiter roars in the radio, that the sun crackles, that the ionosphere sings, that lightning on the far side of the world whistles through the planet's magnetic field in long descending tones. Tesla was listening to a universe of natural transmitters with no catalogue of any of them, and he heard order in it. He was almost certainly right that the signals were real, and almost certainly wrong about what they were. The myth, however, banked the quote. A great inventor heard something from space. That became the foundation stone. The second layer arrived in 1928, when radio operators in Europe recorded echoes of their own transmissions, returning seconds too late from apparent distances far beyond the moon. Those echoes are real, they are documented, and they remain genuinely unexplained to this day. They are also the next item up on this list, number 6, where we will give them the full hour they deserve. For now, note only what the myth did with them. Decades later, enthusiasts reached back, lifted the echoes out of their context, and refiled them as evidence, declaring that the thing delaying the signals was the Black Knight, storing and repeating our broadcasts. The echoes had nothing to do with Tesla, and neither had anything to do with what came next, but the file was growing, and files have gravity. The third layer is where the satellite itself enters, and it enters through a press campaign. In May of 1954, several American newspapers ran a story sourced to Donald Keyhoe, a retired Marine Corps major who had become the country's most famous flying saucer author. Keyhoe claimed the Air Force had detected 2 unknown satellites in orbit around the Earth. It was 3 years before Sputnik. No nation on this planet could place an object in orbit, and every engineer knew it, which made the claim electric. No tracking data was ever produced, no observatory confirmed it, and the Air Force denied it. It is perhaps relevant that Keyhoe had a book about flying saucers to promote that very season, and the story and the promotion traveled together. But the sentence had been printed, and sentences do not decay. Satellites, before anyone had satellites. What gave the 1954 story its whiff of plausibility was a real scientific project running at the same time, and the connection is worth untangling because it shows how myths borrow credit. In the early 1950s, the astronomer Clyde Tombaugh, the man who had discovered Pluto 2 decades earlier, led a systematic telescopic search from New Mexico for small natural moons of the Earth. The reasoning was entirely sober. If our planet held tiny captured moonlets, even ones only meters across, they might serve as natural waypoints for the coming age of spaceflight, and it would be useful to know before anyone launched. Tombaugh's team swept the sky where such objects would move and found, in the end, nothing at all. A null result, carefully obtained by a famous name. But the search itself was reported in the press, and the myth machine performed its favorite trick, converting a search into a discovery. The government has astronomers hunting near-Earth objects, became the government found something and will not say what. Keyhoe's 2 satellites landed in soil that Tombaugh's honest empty-handedness had unintentionally prepared. The fourth layer is the most instructive, because it involves a real object and a real detection. In February of 1960, Time magazine reported that the United States Navy's tracking network had picked up a dark object in a polar orbit around the Earth. This one was true. There was an object, and a polar orbit is exactly the path a reconnaissance satellite wants, sweeping over every point on the planet as it turns below. The trouble was that neither America nor the Soviet Union admitted to owning it. For a few weeks, the dark satellite was a legitimate Cold War mystery. The answer, when it came, was quiet. The object was debris from a Discoverer program launch, an American capsule casing in an orbit nobody had advertised. And here the story earns its place in this video, because the Discoverer program was itself a cover. Under the name Corona, it was America's first photographic spy satellite project, one of the most closely held secrets of the era, and it stayed classified until 1995. For 35 years, the true and boring explanation of the 1960 dark satellite sat in a vault where no debunker could reach it. The vacuum did what vacuums do. The myth expanded to fill it. A fifth layer attached itself in 1963, when the story spread that astronaut Gordon Cooper, orbiting alone aboard his Mercury capsule Faith 7, had seen a glowing green object approach him over Australia, and that tracking stations had seen it too. Cooper was a genuine believer that unexplained objects deserved serious study, and he said so publicly all his life, which made him a perfect witness to borrow. But about this specific story, his answer never wavered. He reported no such object on that flight. He denied the account for 40 years, patiently and repeatedly. The myth kept his name anyway. It had stopped asking permission. And then, in December of 1998, the Black Knight finally got its portrait. The Space Shuttle Endeavour was flying STS-88, the very first assembly mission of the International Space Station. In the payload bay rode the American module Unity, and the mission's task was to mate it to the Russian module Zarya, already in orbit, joining the first two rooms of what would become humanity's outpost. During a spacewalk, astronaut Jerry Ross was working with 4 thermal covers, black insulating blankets sized to fit over the trunnion pins that had anchored Unity in the shuttle's bay. Each was about the size of a coffee table. And one of them got away. It slipped its tether, wandered out of Ross's reach, and drifted, tumbling slowly, black and angular against the bright limb of the Earth. It is worth knowing who lost it, because the man matters to the irony. Jerry Ross was no rookie fumbling in the dark. He was one of the most experienced spacewalkers alive, an astronaut who would eventually fly 7 shuttle missions, the first human being to do so, with a career total of 9 spacewalks spent building and repairing machinery in vacuum. Objects escape on spacewalks constantly, from the most careful hands in the profession, because a pressurized glove is a clumsy instrument and everything not clipped down is trying to leave. The history of spaceflight is a quiet museum of drifted tools, cameras, wrenches, a spatula, an entire tool bag lost during a station repair in 2008 that circled the Earth for months and was bright enough to see with binoculars. The blanket was one more item in that museum. Stay in that moment for a second, because it is the emotional center of this entire entry, and it is almost unbearably ordinary. Ross does not panic, because there is nothing to panic about. A blanket is gone. He reports it on the radio loop in the flat, procedural voice astronauts use for everything, and the crew inside acknowledges it, and Houston logs it, and the checklist moves on. It is a work day. A tool has been dropped, in the world's highest workshop, by a man who cannot chase it. The crew photographed the drifting blanket, as crews photograph everything, and the frames went where every shuttle photograph goes, into NASA's public archive, open to anyone, catalogued under mission and role and frame numbers that you can look up tonight from your bed. The blanket itself was tracked as debris object, and it did what all low, light debris does. Within a few days, its orbit decayed. It touched the upper atmosphere, and it burned. The object in the photographs has not existed since December of 1998. But the photographs existed, and a few years later, someone found them. The black object, strange shape, low orbit, official NASA archive. The frames began to circulate online, labeled as the Black Knight satellite, and the century of unconnected stories snapped around them like a setting. Tesla had heard it. The echoes were it answering. Kehoe's satellites were it being detected. The 1960 dark object was it being tracked. Cooper had seen it. And now, at last, here it was, photographed from a spaceship's window. The picture gave the myth what myths need most: a face. James Oberg, a space engineer and historian who spent a career at Mission Control and another career debunking space folklore, laid the whole thing out in public, patiently, with the debris catalogue entries and the spacewalk transcripts in hand. The crew had announced the loss on a live loop as it happened. The identification was not even difficult. It changed almost nothing. The photograph was too good, and the story was too old, and wanting is stronger than checking. Oberg made one observation about the affair that is worth carrying up the rest of this list. He noted that the believers never asked the crew. 6 people watched that object leave, described it aloud as it happened, and photographed it knowing exactly what it was. And in a quarter century of mythology, the eyewitnesses were the one source the story never consulted. One final absurdity completes the file. The signature detail of the modern myth, that the Black Knight is 13,000 years old, was stolen from a real researcher. That number comes from Duncan Lunan, the Scottish investigator whose remarkable and honest work on the 1928 radio echoes we will meet properly at number 6. Lunan once estimated, from data he later withdrew himself, that a hypothetical probe might have arrived in our neighborhood 13,000 years ago. He never connected any of it to any orbiting satellite. He has spent decades objecting to the graft, and the myth has ignored him for decades, because the myth does not have an author who can be corrected. It has only momentum. So the Black Knight file closes with a verdict no single observer ever intended. There is no object. There never was one object. There was a brilliant inventor hearing an uncatalogued sky, an unexplained echo phenomenon, a book promotion, a classified spy program, a borrowed astronaut, and a lost blanket, 6 true stories melted into one false one. And the lesson it hands the rest of this countdown could not be sharper. The human appetite for a watcher in the sky is so strong that we assembled one out of scraps across 100 years. Every open case above this point on the list must clear that bar. Whatever we find compelling from here on, we have to hold it against our proven ability to build the Black Knight out of nothing. But the next entry was no myth and no blanket. It was a calculation, published by one of the most respected astrophysicists of the Soviet Union, a man whose textbook on the search for cosmic life was co-written with Carl Sagan himself. He measured the motion of a moon, followed the arithmetic where it led, and announced a conclusion that stood in the scientific literature for a decade. The numbers said the moon of Mars was hollow. Number 8. The moon, a Soviet scientist calculated, was hollow. In August of 1877, at the United States Naval Observatory in Washington, an astronomer named Asaph Hall was hunting for moons of Mars and losing heart. He had the finest instrument on Earth for the job, the observatory's 26-inch refractor, then the largest telescope of its kind in the world, and night after night, the space around the red planet showed him nothing. Hall was ready to abandon the search. His wife, Angeline Stickney Hall, a mathematician who had once been his teacher, urged him back to the eyepiece for one more night. On that night, he found a moon, and within the week, he had found a second, closer one. He named them for the sons of the war god, Deimos, meaning dread, and Phobos, meaning fear. It is one of the small perfections of astronomical history that the largest crater on Phobos, a gouge 9 kilometers wide in a body only 27 kilometers long, now carries the name Stickney, for the woman who insisted on one more night. Phobos turned out to be a genuinely odd little world, odd enough that its bare statistics still sound like errors. It circles Mars at an altitude of roughly 6,000 kilometers above the surface, closer to its planet than any other moon in the solar system. For comparison, our own moon keeps a distance of about 384,000 kilometers, more than 60 times farther out. Phobos completes an orbit in 7 hours and 39 minutes, while Mars itself takes more than 24.5 hours to turn once. The moon, in other words, laps its own planet 3 times a day. Seen from the Martian surface, this produces a piece of theater no other world in the solar system offers. Phobos rises in the west, sails against the turning of the sky, and sets in the east, twice in a Martian day, running backward across the heavens simply because it moves faster than the ground beneath it turns. That closeness is not a neutral fact. It has consequences, and one of them founded this entire entry. A moon orbiting below the altitude that matches its planet's rotation is a moon living on borrowed time. The tides work against it. Phobos raises a slight bulge in the solid body of Mars, and because Mars turns slower than Phobos flies, that bulge is always dragged slightly behind the moon, and its gravity pulls backward on it, stealing a whisper of orbital energy with every pass. A moon robbed of energy does something that sounds wrong but is true. It speeds up because it falls inward, and lower orbits are faster. So Phobos is very slowly spiraling down toward Mars, and the pace of that spiral, the so-called secular acceleration, is something astronomers can measure by clocking the moon's position across decades of observations. In 1945, the astronomer Bevan Sharpless did exactly that, combing through more than 60 years of recorded Phobos positions, and announced a measurement. The moon's motion was accelerating, and by his numbers, accelerating briskly. The orbit was decaying fast enough to notice, fast enough to need a cause. And in 1959, one of the most formidable astrophysicists alive picked up Sharpless's number and asked the obvious question: what is dragging Phobos down? Iosif Shklovsky was not a marginal figure, and everything about this entry depends on understanding that. He was one of the founders of modern radio astronomy, the man who explained the strange blue glow of the Crab Nebula as radiation from electrons spiraling in magnetic fields, a member of the Soviet Academy of Sciences, and later the co-author, with Carl Sagan, of Intelligent Life in the Universe, the book that made the scientific search for other civilizations respectable reading on both sides of the Cold War. When Shklovsky did arithmetic, colleagues checked their own. And the arithmetic he published in 1959 ran like this. Suppose the drag on Phobos comes from friction with the outermost wisps of the Martian atmosphere, the only medium available at that altitude. The atmosphere there is almost nothing, a vacuum by any engineering standard. For a drag that faint to bend the motion of a moon as briskly as Sharpless's measurement demanded, the moon must be extraordinarily easy to push. Its density would have to be about 1,000th the density of water. No rock is 1,000th the density of water. No rubble, no ice, no dust ball comes anywhere near it. A body 27 kilometers long with that density could only be one thing. A shell. A thin-walled, empty container, its skin perhaps a few centimeters thick. And Shklovsky said the last sentence out loud. Nature does not build hollow moons. If Phobos was hollow, Phobos was made. He suggested, in print, that the inner moon of Mars might be an artificial satellite, an orbiting station of enormous age, launched by a Martian civilization that no longer existed, its interior long dead, its orbit slowly failing. The idea did not stay in the journals. It ran through the popular press of both superpowers for a decade. It reached the White House science orbit when Eisenhower's missile advisor Fred Singer weighed it seriously enough to publish a critique, and it lodged itself permanently in the imagination of a generation. A dead civilization's space station hanging over Mars visibly falling. It remains, to this day, the highest-ranking artificial moon hypothesis ever advanced by a scientist of the first rank. Notice, before we resolve it, that Shklovsky was not doing anything wrong. This is the part of the entry that matters most. He took a published measurement, applied honest physics to it, refused to flinch at where the arithmetic led, and stated the conclusion conditionally, as a hypothesis exposed to test. That is not pseudoscience. That is the method, operating exactly as designed, on an input that happened to be faulty. The fault was upstream, in the number itself. Because the resolution, when it came, arrived in two clean steps. First, better data. As tracking improved through the 1960s and 70s, and especially once spacecraft began photographing Phobos directly, the secular acceleration was remeasured, and Sharpless's value turned out to be roughly twice the true one. The moon is falling, but at about half the announced pace. Second, better theory. The true, smaller acceleration needs no atmosphere at all. The tidal mechanism, the lagging bulge in the body of Mars pulling backward on its moon, accounts for the entire measured spiral, acting on a completely ordinary, solid Phobos. The hollow moon was never needed. It had been conjured by a factor of 2 in a difficult measurement, amplified through honest arithmetic into the most romantic wrong answer in planetary science. The spacecraft that did the weighing have a history of their own with this moon, and one chapter of it feeds the mythology to this day, so it belongs in the honest record. In 1988, the Soviet Union launched 2 ambitious probes, Phobos 1 and Phobos 2, the most capable machines it had ever sent toward Mars, designed to study the planet and then hover over its inner moon, lowering instruments to the surface. Phobos 1 was lost on the way out, killed by a single erroneous command uploaded from the ground that shut down its attitude control. Phobos 2 made it. It reached Mars in January of 1989, studied the planet and its moon for weeks, and returned dozens of images of Phobos, including a few showing a long elliptical shadow gliding across the Martian surface, which is exactly what the shadow of a potato-shaped moon looks like when it falls on a curved landscape at an angle. Then, in March, days before its closest rendezvous, the spacecraft's failing onboard computer lost attitude control during a routine imaging turn, the antenna wandered off Earth, and contact was never recovered. 2 probes, 2 ordinary engineering deaths of a kind that has claimed dozens of Mars missions from every nation that has tried. The mythology, of course, kept the shadow pictures and discarded the engineering, and you can find the last transmissions of Phobos 2 presented tonight on the same internet that hosts the Black Knight, as evidence that something at Mars objected to being photographed. The pattern from number 9, assembling a watcher out of scraps, does not stay on Earth. When spacecraft finally weighed Phobos, by measuring how its faint gravity tugged them during close flybys, the real number came in at about 1.86 grams per cubic centimeter, roughly half the density of ordinary rock. Not hollow, but not solid stone either. The modern reading is that Phobos is a rubble pile, a loosely consolidated heap of shattered rock, holding perhaps 1/4 to 1/3 of its volume as empty pore space, possibly with buried ice woven through its depths. Shklovsky's ghost station dissolved into something less dramatic and, in its own way, harder to explain. Because the closing of the artificial file opened a natural one that has never been closed, and this is why Phobos ranks this high on a list of open questions. We still do not know where this moon came from. Pause on how strange it is that the question is still open, because Phobos is not some dim speck at the edge of the solar system. It is the moon of our next-door neighbor, photographed at close range by a parade of spacecraft across 5 decades, Mariner 9 in the 1970s, the Viking orbiters, Mars Global Surveyor, Mars Express, which has flown within a few dozen kilometers of its surface, the reconnaissance orbiters that map it in color from above. We know its shape to fine precision. We have measured its temperature through the day and night, mapped the strange bluish and reddish provinces of its surface, and clocked its slow tumble to fractions of a second. And with all of that in hand, planetary science still cannot answer the first question anyone would ask about it. Where did it come from? There are two candidate origin stories, and each one fails in a different place. The first says Phobos is a captured asteroid. Its surface reflects light the way the dark, carbon-rich asteroids of the outer belt do, so perhaps Mars simply caught one. The trouble is the orbit. A captured body should arrive on a wild, tilted, stretched path, and Phobos rides in a nearly perfect circle, exactly above the Martian equator, the least likely orbit for a capture to produce. The second story says Phobos condensed from a ring of debris blasted off Mars itself by a giant impact, the same family of violence that built our own moon. That explains the tidy orbit beautifully, and then stumbles on the surface, which does not look like recycled Mars. Two stories, each explaining what the other cannot. Add the strange families of parallel grooves raked across the moon, hundreds of channels that may be stretch marks from the tides, or scars from debris that once orbited Mars, or the tracks of boulders rolling home after the Sputnik impact, and Phobos keeps a genuinely open file in 3 separate drawers. And because the internet never met an ambiguity it could not decorate, Phobos also carries a monolith. Among the images returned by the Mars Global Surveyor spacecraft in the late 1990s is a photograph showing a single angular boulder, roughly 85 meters tall, standing alone on the moon's surface and throwing a long shadow. Geologically, it is an unremarkable block of ejecta, a chip knocked loose by an impact and left standing, the kind of lonely rock Mars itself displays by the thousand. But it photographs like a deliberate object, and it collected a famous piece of free advertising when the Apollo astronaut Buzz Aldrin, in a 2009 television interview, urged the public to visit the monolith on Phobos. He meant it as an enthusiast of exploration. The clip circulates to this day, stripped of that context, doing steady work for the artificial moon story Shklovsky retired half a century ago. So come stand on it, for a moment, this moon that so many hands have tried to make mean something. You are on the rim of Sputnik crater, and the ground under your boots is dark grey, darker than asphalt, a powder of shattered rock that has known no rain for 4 billion years. You weigh almost nothing here. The gravity of Phobos is about 1/2000th of Earth's, so gentle that a firm jump would put you into space, and so you move carefully, the way divers move. The grooves run past you toward the near horizon, long parallel furrows like the wake of enormous fingers, and the horizon itself is absurdly close, a few kilometers, curving visibly, the whole world small enough to walk around in a long day. And then you look up, and there is Mars. Not a light in the sky, a ceiling. The planet fills a third of the heavens above you, rust and amber and dust storm white, so close you can watch the shield of Olympus Mons rotate past, so close it seems in danger of falling on you, though the truth, of course, runs the other way. You are the one falling. Every 7 hours and 39 minutes you circle that ceiling once, and every year you are a few centimeters lower. Standing here, feeling that patient descent in your mind, you understand Shklovsky completely. A dying orbit, an impossible lightness, a world hanging too close overhead. Of course, the arithmetic whispered that someone built this. The genuinely strange truth is that no one did, and it is falling anyway. The fall, incidentally, is not a metaphor, and it has a timetable, which is more than most items on this list can say. The tides that resolved the mystery are still working, and their endpoint is scheduled. In somewhere between 30 and 50 million years, Phobos will descend to the altitude where the gravity of Mars stresses it beyond its strength, and the rubble pile will come apart. For a while, Mars will wear its inner moon as a ring, a band of tumbling debris grinding itself finer with the years, and then the ring will rain down piece by piece onto the planet, and the sky of Mars will be empty of fear. Deimos, dread, orbiting farther out and drifting slowly away, will remain. Any observers on Mars in that distant era, whoever or whatever they turn out to be, will inherit a ringed world and a mystery in reverse, a planet wearing the ground-up remains of a moon they never saw whole. Rings, it turns out, are not permanent jewelry. They are events, caught mid-fall, and Mars is simply scheduled for one. Before any of that, we are going to hold pieces of this moon in laboratories on Earth. The Japanese space agency JAXA has built a mission called Martian Moons E-Exploration, MMX for short, prepared for launch in the current window, and its plan is the direct descendant of every question in this entry. MMX will fly to Mars, settle into orbit alongside Phobos, study it exhaustively, and then perform something never attempted at the moon of another planet. It will land, collect samples of that dark grey surface, carrying a small rover contributed by the French and German space agencies to scout the ground, and then it will bring the samples home, with the return capsule scheduled to deliver Phobos to Earth in the early 2030s. In those grams of powder, the origin question finally meets its test. If the sample reads like the outer asteroid belt, Mars caught its moon. If it reads like Mars, the moon was born in an impact. A century, nearly, after Shklovsky followed a faulty number to a hollow shell, the answer to what Phobos actually is, asteroid or wreckage, visitor or native, will come down out of the sky in a capsule into the hands of a generation that had not been born when he did the sum. There is the human stake of number 8, and it is worth holding on to tonight. A serious scientist's honest mathematics permitted a dead civilization's space station to hang over Mars for a decade, in the pages of respectable journals, and the machinery of science neither punished the idea nor protected it. It simply kept measuring until the truth emerged, and the truth turned out to be a stranger, slower story about a doomed heap of rubble that no one can yet explain. The next object on this list compressed that same arc into a smaller package and a shorter fuse. It was not a moon, and it was not far away. It was 10 meters of something, sharing Earth's own orbit, and the paper that called it a probe was not written in the 1950s. It passed within reach of our telescopes twice in living memory, and the first time it caught us completely unprepared. Number 7. The first object formally proposed as a probe. On the night of the 6th of November 1991, James Scotty was alone on Kitt Peak, a mountain in the Arizona desert crowned with telescopes, working a shift at an instrument called Spacewatch. Spacewatch was something new in the world. Its telescope was old and modest, a 0.9-meter instrument dating from the 1920s, but bolted to it was one of the first electronic cameras ever set loose on the whole sky, feeding software that compared image to image and flagged anything that moved. For all of astronomical history until then, asteroids had been found by human eyes, straining over photographic plates. Spacewatch was the beginning of the era we live in now, when machines watch the sky continuously and people examine what the machines catch. And on that November night, the machine caught something that would take 26 years to answer. The object was small, perhaps 10 meters across, the size of a bus, and it was designated 1991 VG. Objects that size cross the sky all the time, and almost all of them are instantly boring. This one was not, and the trouble began, as it did with 2020 SO, with the orbit. 1991, VG was circling the Sun on a path astonishingly similar to Earth's. The same size of orbit, nearly the same shape, nearly the same tilt, a companion in our own lane. You already know, from number 10, why that is suspicious. Earth's lane cleans itself. An object sharing it gets gravitationally shoved at every encounter, and over a few thousand years, it is scattered onto some other path. Whatever 1991 VG was, it had not been in that orbit long. It had recently arrived, and there were only a few kinds of place it could have arrived from. A month after discovery, on the 5th of December 1991, the object swept past Earth at about 450,000 kilometers, a little beyond the Moon's distance. Observers watching it closely saw its brightness swing sharply and fast, flickering on timescales of minutes. That flickering is information. It is the signature of an elongated body tumbling end over end, showing the Sun first its narrow face and then its broad one, or else of something with flat, mirror-like surfaces, catching the light and losing it. Natural rocks tumble, so the flickering proved nothing by itself. But flat reflective panels flicker too, and everything human beings launch is covered in flat reflective panels. The observations were filed, the object receded, and the file stayed open. Because there was an obvious, comfortable explanation, and it deserved to be checked first. By 1991, humanity had been throwing hardware beyond the Moon for 3 decades. Every deep space mission rode an upper stage, and many of those stages, their work done, had been abandoned on orbits around the Sun, exactly the kind of orbits that could one day drift back to meet us. 2020 SO, remember, turned out to be precisely such a wanderer coming home. The natural first guess was that 1991 VG was the same story, a spent booster from the Apollo era, or some planetary launch, returning on schedule to the neighborhood that built it. The guess was so plausible that most astronomers simply assumed it and moved on. And the guess deserves respect, because 11 years later it came true for a different object, and the story of that object is the perfect control case for this one. In September of 2002, an amateur astronomer named Bill Young discovered a faint body apparently orbiting the Earth, catalogued as J002E3. An object in a distant Earth orbit that nobody had launched recently was a puzzle of exactly our kind, and for a few weeks it ran the same gauntlet of hypotheses. Then spectroscopy found its surface reflecting light the way titanium dioxide paint does, the white paint NASA used on Saturn rockets, and the orbital rewind pointed at Apollo 12. The object is believed to be that mission's spent third stage, the S-4B, launched in November of 1969, misplaced into a wrong solar orbit after its lunar flyby, and returning every few decades to be temporarily recaptured by the planet that built it. It has since drifted out again, and it is expected back. So, the space age really does send its debris home. The debris really does get mistaken for mystery objects, and the tests really do unmask it, by paint, by orbit, by bookkeeping. That is the standard against which 1991 VG has to be measured, and the reason the next step in this story matters. One astronomer did not assume. He checked. Duncan Steele, an asteroid specialist then working in Australia, sat down with the actual launch records of the space age and asked a bookkeeper's question. Which specific deep space launches left hardware on heliocentric orbits, and do the orbits of any of that hardware return to Earth's vicinity in November of 1991? He worked through the candidates, the lunar missions, the planetary missions, the stages and shrouds and adapters, and the answer he published in 1995 in The Observatory, one of the oldest refereed astronomy journals in the world, was that none of them fit. No catalogued piece of human hardware on a purely gravitational path should have been where 1991 VG was, when it was. The comfortable explanation had a hole in its paperwork. And then Steele did the thing that placed this object 7th on our countdown. Having eliminated the boosters he could account for, he stated the remaining possibilities plainly, and one of them, he argued, had to be taken seriously. 1991, VG was a candidate alien probe. He gave the idea a framework and an acronym, SETA, the search for extraterrestrial artifacts, and he anchored it to a respectable lineage. Back in 1960, the radio astronomer Ronald Bracewell had published a short paper in Nature arguing that if civilizations wish to find one another, beacons of radio waves are the expensive way, and the economical way is machines. A long-lived robotic probe sent to a promising star system could park itself patiently in orbit, wait for radio chatter to emerge from a young civilization, and then announce itself. Such machines, Bracewell probes, would by definition be small, quiet, and easy to miss, and the natural place to look for one is exactly where station keeping is cheapest, in orbits that shadow the local planet's own. An Earth-like heliocentric orbit, the very lane where Scotty's software had flagged a 10-meter flickering something. It is worth being precise about what Steele's paper was, because the distinction is the soul of this entire video. It was not a claim that aliens had been found. It was a demonstration that a specific, testable hypothesis could not yet be excluded, published in a refereed venue by a working scientist who laid out exactly what evidence would settle the question either way. For its era, it was nearly unique. Respectable careers had been built on searching for radio signals, but pointing at a specific catalogued object in the sky and saying, in print, this could be an artifact, and here is how to check, was a different kind of nerve. The check, however, had a problem, and the problem was time. 1991, VG had already left. Its orbit would not bring it back to Earth's neighborhood for a quarter of a century. Steele's argument had a statistical spine worth restating, because it was never merely a shrug at missing paperwork. He counted. The number of deep space launches between 1958 and 1991 was small, a few hundred, and the subset that abandoned hardware on sun-circling orbits smaller still. For one of those pieces to return, by pure gravitational coincidence, through the tiny keyhole of time and space where 1991 VG appeared, was a long odds event, and the odds got longer the more carefully he reconstructed each candidate's path. The alternative candidates were not much kinder. Natural objects in such orbits were, by the survey statistics of the day, expected to be vanishingly rare. He was left holding an object too odd for the catalogue of nature, as then understood and unclaimed by the catalogue of engineering. His probe suggestion was, in the strict sense, the honest remainder of an elimination. What the next 26 years supplied was the missing piece of the natural catalogue. The hypothesis went into a drawer, and the drawer stayed shut while the world changed, while the internet arrived, while surveys like the one at Spacewatch multiplied and industrialized, while a 10-meter question mark moved through the sky, patient as arithmetic, telling no one anything. Hold on to that image, a question mark moving through the sky. It will come back near the top of this list, attached to an object far stranger than this one, and when it does, the difference between the two endings is the whole story. In the summer of 2017, right on schedule, 1991, VG came home to be examined, and this time, the examiners were ready. Telescopes far more capable than Spacewatch's old reflector tracked it for months. The definitive analysis was published by Carlos and Raúl de la Fuente Marcos, two dynamicists in Madrid who specialize in the intricate gravitational choreography of objects near the Earth, in the monthly notices of the Royal Astronomical Society. Their verdict came in two parts, and each part quietly closed a door Steele had left open. First, the orbit. Integrated carefully through time, forward and backward, the path of 1991 VG turned out to be complicated, genuinely unusual, and completely natural. The object belongs to a small population of bodies in Earth-like orbits, sometimes called Arjuna asteroids, that engage in a slow gravitational dance with our planet. They drift ahead of Earth, fall behind, swap between slightly wider and slightly narrower orbits at each close pass, and occasionally, when the geometry aligns, get temporarily captured as mini-moons for months at a stretch. The analysis showed 1991 VG had likely done exactly this before, and would do it again, with no engine, no course corrections, no intent, just gravity performing one of its more intricate standard numbers. The name of the family is its own small poem. Tom Gehrels, the Dutch-American astronomer who ran the Spacewatch project, called these Earth-shadowing bodies Arjunas, after the archer of the Sanskrit epics, and the informal name stuck in the literature, a rare case of the Mahabharata contributing to orbital dynamics. Membership has grown slowly because the objects are so hard to catch, small, faint, and only observable during brief windows when their slow drift brings them past us. Each one found makes 1991 VG look a little less like a visitor and a little more like a local. What had looked in 1991 like an orbit too Earth-like to be innocent turned out to be a known, if rare, dynamical family. A few dozen such objects have been catalogued since. In 1991, this was among the first, which is precisely why it looked so alone and so deliberate. Anomalies, it turns out, are often just the first member of a class to be discovered. Second, and decisively, the physics. Remember the instrument from number 10, the sharpest test in this video. When astronomers measured the trajectory of 2020 SO, they found sunlight pushing it off course, betraying a hollow, lightweight shell. The 2017 observations of 1991 VG were precise enough to run the same test. The result was silence. No measurable push. Sunlight presses on 1991 VG, and 1991 VG does not care, which means it is not a thin-walled artifact, not a panel, not a sail, not an abandoned stage. It is dense. It is, by every measurement we can make, a compact 10-meter rock, tumbling exactly as rocks tumble. Combined with the natural dynamics, the verdict was clean. The search for extraterrestrial artifacts at this particular address was over. Steele himself accepted the conclusion with the good grace of a scientist whose hypothesis had done its job by being testable. And yet number 7 does not close all the way, which is why it sits above the myths and below the mysteries. The probe reading is retired, but nobody has ever assigned 1991 VG an origin. A 10-meter rock does not condense out of nothing into Earth's lane. It came from somewhere, recently, and the candidates each carry a small strangeness. It may be an ordinary near-Earth asteroid that random gravitational encounters walked, step by step, into this improbable orbit. It may be a fragment of the Moon itself, blasted off by an impact and left circling the Sun in Earth's company, a possibility made respectable by the later discovery that at least one other co-orbital companion of Earth, the quasi-satellite Kamo-Oalewa, reflects light exactly the way lunar rock does, and is now the target of a sample return mission on exactly that suspicion. pieces of the moon really do haunt Earth's lane. Whether 1991 VG is one of them, no one knows, because no one has pointed the right instruments at it during the right pass. It will be back. Its dance guarantees that, and some future apparition will likely settle the last of it. There is even a practical incentive now that did not exist in 1991. Objects in Earth-like orbits are, by the cold arithmetic of rocketry, among the cheapest destinations in the solar system, easier to reach in terms of fuel than the surface of our own moon. Mission planners studying asteroid mining and sample returns keep lists of such accessible bodies, and the Arjunas sit near the top. The bus-sized rock that was once accused of being a probe may eventually receive a probe of ours, which would be a tidy way for the question mark to end its career. So the scoreboard after number 7 reads like this. An object was flagged. A scientist refused to wave it through without checking the books. The books came up short, and a probe hypothesis stood untested in the literature for 26 years, not because anyone was credulous, but because the solar system runs on a slower clock than human curiosity. When the test finally came, nature won the case, and the method that won it, patient orbital analysis plus the radiation pressure test, was sharpened for the next customer. Science does not lose these encounters even when the answer is mundane. Every retired candidate calibrates the instruments for the one that will not retire. The next entry on this list is not an object you can point a telescope at. You cannot photograph it, orbit it, or wait for it to come back around, because it was never a thing in the sky at all. It is an echo, recorded by serious physicists with the best instruments of their age, and what it seemed to be echoing from was a place where nothing should have been. It has been answering our radio signals, late, since before radio was old enough to vote, and after nearly 100 years, we still do not know what is doing the answering. Number 6. Radio signals that came back too late. In the summer of 1927, a Norwegian engineer named Jørgen Hals sat listening to the radio near Oslo and heard the sky repeat itself. He was tuned to one of the marvels of the age, the powerful shortwave station PCJJ in Eindhoven in the Netherlands, whose broadcasts reached around the planet. Reaching around the planet, in fact, was the point of what Hals noticed first, and that part was understood. A shortwave signal, bouncing between the ionosphere and the ground, can circle the entire Earth in about 1/7 of a second and arrive again at the receiver as a faint echo trailing the original. Radio engineers knew the round-the-world echo well. It was almost a parlor trick, a way of hearing the size of the planet. But behind the familiar echo, Hals heard something else. A third arrival. The same signal, unmistakably, coming in again roughly 3 seconds late. 3 seconds should not have been possible, and the reason is nothing more complicated than the speed of light. Radio waves travel at the same speed light does, about 300,000 kilometers every second. An echo delayed 3 seconds has therefore traveled, out and back, nearly 1 million kilometers, which places the reflecting surface almost 500,000 kilometers away. The Moon, the only large object out there, orbits at 384,000 kilometers, and a moon bounce echo, which is a real thing radio operators would later use routinely, takes about 2.6 seconds. Hals's echoes were arriving later than the Moon allows, and on many occasions, much later. And to feel how radical that was in 1927, remember what the upper sky was to the people of that decade. The ionosphere itself, the electrified layer that makes shortwave radio work at all, had only just been confirmed to exist. Edward Appleton performed the measurements that proved the reflecting layer was real in 1924, work that would earn him a Nobel Prize, and the physics of how the sun builds and dissolves that mirror over the course of each day was being worked out in real time. Radio operators were explorers then, in the plainest sense. Every increase in transmitter power revealed new behavior in a sky nobody had finished mapping. Bouncing a signal off the moon deliberately, the trick that would later become routine, was 2 decades away, achieved only in 1946 when the United States Army's Project Diana fired radar at the lunar surface and caught the return 2.5 seconds later, to public astonishment. HALS, in other words, was reporting echoes from beyond the moon at a time when reaching the moon with radio was still considered close to science fiction. The report could easily have been dismissed. What saved it was who he told. Something appeared to be receiving humanity's broadcasts, holding them and sending them back from beyond the moon's distance. Or something was storing them closer in by a mechanism nobody could name. Neither option had any business existing. HALS did the correct thing. He wrote to the most qualified man in the country, Carl Sturmer, Norway's great mathematical physicist. Sturmer was a world authority on the Northern Lights, the man who had explained how charged particles from the sun thread themselves along Earth's magnetic field lines, and he had spent his career photographing and calculating the luminous machinery of the upper atmosphere. If anyone alive could judge whether the Earth's own plasma envelope might swallow a radio signal and cough it back seconds later, it was him. Sturmer listened, took HALS seriously, and escalated. He contacted Balthasar van der Pol, the director of research at the Philips laboratories in Eindhoven, the very home of station PCJJ. Van der Pol was himself a formidable figure, a physicist whose work on oscillating circuits was foundational, whose name lives on in the mathematics of oscillation to this day. This is the caliber of the people in this story, and it matters, because what happened next was not an anecdote. It was an experiment. On the 11th of October 1928, Van der Pol arranged for the Eindhoven transmitter to send a special program, not music or speech, but a clean scientific signal, 3 short pulses repeated at fixed intervals, unmistakable and time-stamped. In Oslo, Sturmer and HALS sat at the receiver with a stopwatch and waited to hear whether the sky would answer. Put yourself in that room for a moment, because it is one of the quietly eerie scenes in the history of physics. It is a cold October evening on the edge of the North Sea. The receiving equipment glows, valve amplifiers warming the dark like embers, and the room smells of hot dust and electricity. The dots arrive from Eindhoven, crisp and immediate. A 1/7 of a second behind them comes the whisper of the same dots, having circled the world. Then silence. 1 second of it, 2, 3, the stopwatch ticking in Sturmer's hand, and then, out of the static, softly, the dots come back. Not distorted beyond recognition. The same 3 dots, patient and deliberate, as if the sky had listened to the message, considered it, and repeated it back to prove it was paying attention. Sturmer would later publish the log of one especially productive session, and the bare numbers still read strangely, a column of delays with no rhythm, as if drawn from a hat. On some evenings the wait was 3 seconds, on others 5, or 8, or 11. The observers logged echo after echo across weeks of sessions, delays scattering between 3 seconds and half a minute, with no fixed pattern anyone could extract. A 30-second delay, taken at face value as a reflection, puts the mirror 4.5 million kilometers away, a dozen times the distance of the moon, in a region of space that contains, as far as anyone knew or knows, nothing at all. The observations were serious enough to be reported in Nature, among the most selective scientific journals in the world, and they were repeated and confirmed by other stations in the months that followed. French investigators caught echoes in 1929 during their own organized campaign. Independent listeners in several countries logged the effect on different frequencies from different transmitters, which is important because it retired the easiest objection that something was wrong with one receiver in Norway. Whatever produced the delays was available, at least occasionally, to anyone with suitable equipment on the night side of the planet. The record from that first wave of work amounts to dozens of well-attested echo events with delays beyond any conventional propagation path, gathered by the leading radiophysicists of the era using the best characterized transmitters on Earth. And then, having announced itself, the phenomenon did the most maddening thing an anomaly can do. It became unreliable. Sessions that had produced echoes fell silent. Campaigns organized to chase it caught fragments or nothing. Through the 20th century, long-delayed echoes settled into a strange half-life, sporadically reported by radio amateurs and occasionally by professionals, well enough documented that reviews of the subject treat the core 1928 observations as trustworthy, and never once behaving stably enough for a definitive experiment. Explanations were proposed, and each one leaks. Perhaps the signals were ducted and slowed in the plasma of the ionosphere, crawling along magnetic field lines at a fraction of light speed before escaping, a mechanism that can plausibly manufacture fractions of a second and strains credibility at 8 seconds and breaks at 30. Perhaps the signals traveled out along the field lines of Earth's magnetosphere to distant plasma boundaries and returned. Perhaps they were stored, converted at a plasma boundary into slow-moving waves, and later reconverted, radio put into a bottle by the magnetosphere and uncorked seconds later. Each mechanism explains a slice of the record. A century on, none explains the whole of it. The modern keeper of this problem is, fittingly, another Norwegian, the signal processing professor Sverre Holm in Oslo, who has spent years collecting amateur reports and sorting the whole century of echoes into categories by delay and plausibility. His sober conclusion is roughly this: the shortest delays, fractions of a second beyond the world echo, have credible ionospheric explanations. The middle range is contested territory where magnetospheric ducting might, with some straining, be made to work. And the long tail, the echoes of many seconds that Sturmer and van der Poel documented most carefully, remains without an accepted mechanism at all. The honest summary in the technical literature, a full century after a man in Norway first heard the sky stutter, is that long-delayed echoes are real and unexplained. Into that standing silence, in 1973, stepped a Scottish researcher named Duncan Lunan, carrying an idea we have already met tonight. Ronald Bracewell's patient robotic envoy, the probe that parks itself in a solar system and waits for radio to be invented, had one more property worth remembering. Bracewell suggested that such a machine, wanting to be noticed, would do the simplest attention-getting thing possible. It would echo our own signals back at us. A civilization that hears its own broadcast returned from empty space, the reasoning went, cannot help but investigate, and the varying delays might even carry information, a message written not in words but in time. The economics behind Bracewell's idea are worth 30 seconds because they explain why sober engineers keep returning to it. A radio beacon, to be heard across interstellar distances, must shout continuously in all directions for millions of years, an appalling energy bill paid up front with no guarantee anyone is listening. A probe pays differently. Build it once, aim it at a promising star, and let it coast and wait, spending almost nothing. It carries the conversation to the customer, answers in seconds instead of centuries, and can hold its message until the exact moment a civilization becomes able to hear it, which is the moment it invents radio. If contact is ever attempted between worlds, this argument says, the first artifact involved will probably be a small, patient machine rather than a beam of light, and the first evidence will look less like a message and more like an anomaly in the behavior of our own signals. Lunan read the 1928 records with that thought in mind. Sturmer and van der Pol had logged every session, the delay of every echo, dry columns of seconds in old journals. Lunan graphed them. He plotted the echoes of one session as points, delay against sequence, and when he oriented the chart a particular way, the points arranged themselves, he realized, into something he recognized. A star map. The pattern of the constellation Boötis, the herdsman, drawn in echo delays, with every star in its familiar place except one. Epsilon Bootis, a bright double star in the herdsman's belt, sat displaced from where it belonged. Lunan read the displacement as the signature, the sender pointing at itself. His interpretation, published in the Journal of the British Interplanetary Society, said that a probe stationed near the Moon, at one of the stable points of the Earth-Moon system, had been caught in 1928, performing exactly the maneuver Bracewell described, and that its home was Epsilon Bootis, and that the geometry of the map suggested it had arrived 13,000 years ago. For one strange season, the world took the bait whole. Time magazine ran the story under the headline, "Message from a Star." Newspapers around the world repeated it. Lunan presented the work to engineering societies and fielded questions from broadcasters on several continents. The magazine Analog, the most respected science fiction and science venue of its day, ran his full analysis in January of 1974 under the title Space Probe, from Epsilon Bootis, with a question mark that most readers ignored, and Lunan spent years afterward being asked about the probe every time his name appeared in print. Radio operators dusted off equipment and listened for new echoes to answer. There was even brief talk of transmitting a reply toward the herdsman, on the theory that a machine that had waited 13,000 years deserved the courtesy. It remains, half a century later, probably the closest thing in history to a mainstream moment in which humanity believed it had received and decoded a message from an alien machine, sourced not from a tabloid, but from careful 1920s data reanalyzed by a named researcher who showed his work. And that is precisely why what happened next matters more than the map ever did. Lunan kept working. He re-examined his own analysis, tested the star map against better catalogues and stricter statistics, and found it did not survive. The correlation was an artifact of selection, the kind of pattern that echo delays scattered by an unknown natural process can produce for an eye that is searching for constellations. And he said so. Publicly, in print, at the cost of the most famous idea he would ever have, Duncan Lunan withdrew the Epsilon Bootis interpretation. He did not slink away. He continued a long career in space science writing, and he has spent part of every decade since patiently correcting people who still quote the map as fact, and objecting, as we heard at number 9, to the theft of his 13,000 years by the Black Knight mythology. In a video full of hypotheses, his remains the only one on this list killed by its own author, which is the most honorable death available to an idea. But mark what his retraction did not do. It did not explain the echoes. Strip away the star map, and the 1928 observations stand exactly where Sturmer and van der Pol left them, documented in Nature, replicated across stations, and unexplained. The mirror 4.5 million kilometers away is still required, or else the bottle in the magnetosphere that holds radio for 30 seconds, and neither has ever been produced. Radio amateurs still occasionally log an echo seconds late and file it with a shrug into a century-old drawer. And here is the detail that keeps the file warm rather than cold. Unlike almost every other mystery on this list, this one is, in principle, an experiment anyone can rerun. The transmitters exist, more powerful than anything van der Pol commanded. The receivers exist, in millions of homes. Digital timing has replaced the stopwatch, and software can monitor for anomalous returns around the clock without a human ear. Occasional organized listening campaigns have been proposed and a few attempted, and the phenomenon, true to its century of character, has declined to perform on demand. An effect that appears only when unwatched sits in an uncomfortable place for science, not because anyone doubts the 1928 records, but because the tools of proof require repetition, and the sky will not repeat itself on schedule. The artificial explanation is dead by honest suicide. The natural explanation has never fully arrived. That combination, an effect that is real, recorded, and ownerless, is what an open file actually looks like, and it earns the echoes their place above every solved case on this countdown. The human stake here is a peculiar one, and worth saying gently. Everyone now listening to this has grown up inside a planet-sized web of transmissions, and we assume the sky between worlds is a passive thing, a silence our signals cross. The long-delayed echoes are a 100-year-old suggestion that the assumption might be incomplete, that something in the near-Earth environment, whether a plasma trick we have not mastered or something we have not imagined, can catch what we say and say it back. The next mystery on this list is also, in its way, an archive problem, a record made by careful professionals with the best instruments of their era, showing something that should not be there. But it is not made of sound. It is a photograph, a single pair of glass plates exposed at Palomar Observatory in 1952, 50 minutes apart. In the first exposure, 3 stars. In the second, none. Number 5. 3 star-like objects that vanished in under an hour. To understand the next mystery, you first have to understand what a sky survey was in 1952, because the entire case lives inside 2 pieces of glass. In that era, the state-of-the-art in mapping the heavens was the Palomar Observatory Sky Survey, one of the most ambitious scientific undertakings of its century. Night after night, the 48-inch Schmidt telescope on Palomar Mountain in California photographed the sky section by section onto large glass plates coated in photographic emulsion, each plate capturing a square of sky about 6 degrees on a side, sown with tens of thousands of stars and galaxies. The survey photographed each field twice in close succession, once on a blue sensitive plate and once on a red sensitive plate, so that astronomers could compare the 2 colors. Those paired exposures, taken minutes to an hour apart, were meant to measure the colors of stars. What they accidentally created was a trap for anything in the sky that changes fast, because whatever appears on one plate of a pair and not the other must have appeared or vanished in the gap between them. The scale of the survey is worth feeling before we look at one plate in particular. The project, funded in part by the National Geographic Society, ran from 1949 into the late 1950s and produced nearly 2,000 plates covering the entire sky visible from California. For half a century afterward, those plates were the reference map of the universe. When astronomers discovered a new object, they checked the Palomar plates to see if it had been there in the 50s. When they needed a comparison image for a supernova, a quasar, an asteroid recovery, they pulled the Palomar plates. Whole careers, whole subfields, rested on the working assumption that what the plates show is what the sky contained, and that assumption earned its keep millions of times over. The plates were eventually digitized, every star and smudge converted to data anyone can query, and it was that digitization that made the following discovery possible, because no human being was ever going to recheck 2,000 plates by eye, point by point, against the modern sky. Software could. And when software finally did, a tiny fraction of the old sky turned out to be missing. On the night of the 19th of July, 1952, the telescope photographed a field in the constellation Pegasus. On the red plate, among the thousands of ordinary points of light, there are three that should not be there. They are bright, around 15th magnitude, which for this instrument is not faint at all, well above the survey's limits, the kind of brightness a respectable star displays. They are sharp, clean, star-like points, indistinguishable in their profiles from the true stars around them. And they sit remarkably close together, all three inside a circle about 10 arcseconds across, which is a patch of sky far smaller than the full moon, tighter than almost any grouping of genuine stars you will ever find. On the second plate of the pair, exposed less than 50 minutes later, they are gone. Not faded. Not smeared. Gone, without residue, while every ordinary star around them sits exactly where it was. Run through what the sky is allowed to do and watch each permission fail. Stars do not turn off. Even the most violent variable stars, the flare stars and cataclysmic binaries, decline over hours and days and leave a faint star behind at minimum. And here, there is nothing beneath the vanishing point, on that night or any night since. Three separate variable stars packed into 10 arcseconds, erupting and collapsing in synchrony inside 50 minutes, is not a phenomenon astrophysics has ever catalogued. Asteroids fail in the opposite direction. Solar system objects move, and at typical asteroid rates, a body photographed over the long exposure would draw a visible trail on the plate, not a clean point, and would in any case still exist on the second plate, merely displaced. These are not trails. Meteors are far too fast, satellites did not exist, and aircraft lights over a long exposure paint streaks, not stellar points. The plate pair simply asserts, with the flat confidence of a legal document, that three star-like lights occupied a tiny patch of Pegasus for some portion of one exposure and did not occupy it 50 minutes later. There is one more constraint hiding in the exposure itself, and it tightens the mystery rather than loosening it. A survey plate is not a snapshot. The shutter stays open for tens of minutes, accumulating light, which is why faint galaxies register at all. A source that shines steadily through the whole exposure builds a strong image. A source that shines for only a fraction of the exposure builds a weaker one, diluted by all the empty minutes. For the three transients to register at a healthy 15th magnitude on a long exposure, either they shone at that brightness for most of the exposure and then extinguished completely before the next one began, or they shone far more brilliantly for a short interval, seconds perhaps, and the plate recorded the average. The second reading is exactly what a glint looks like. It is also, if the sources were astronomical, a demand for a burst mechanism of remarkable violence at any distance beyond the atmosphere. Either way, the plate is telling us about something abrupt, and abrupt is the one quality the quiet, deep sky almost never displays. The modern investigation of this case is recent and serious. A team led by Enrique Solano of the Spanish Virtual Observatory with Beatriz Villarroel of the Nordic Institute for Theoretical Physics and colleagues published the analysis in 2023 in the monthly notices of the Royal Astronomical Society. They did what modern astronomers do to old mysteries. They dug through every subsequent image of that field across 71 years of surveys, each generation deeper than the last, and found the three sources absent from all of them. Then they applied for time on the Gran Telescopio Canarias, the largest single optical telescope on Earth, 10.4 meters of mirror in the Canary Islands, and in April of 2023, they stared at the empty coordinates down to magnitude 25.5. That number deserves a comparison. A 15th magnitude source is within reach of a good amateur telescope in a backyard. Magnitude 25.5 is the domain of the largest mirrors on the planet, gathering photons for long minutes, faint enough that the light arriving per second from such a source could be counted in individual photons. Between the two lies a factor of roughly 10,000 in brightness. If those three lights were stars that somehow dimmed, they dimmed by a factor of more than 10,000 inside 50 minutes and have held there for 3/4 of a century. No known star does anything within 1,000 miles of that. So the explanations on the table are all exotic, and the paper walks through them honestly. Option 1. Gravitational lensing. A single distant flaring source could, in principle, be split into 3 images by the gravity of a massive object sitting almost exactly along the line of sight, and the images would appear and disappear together as the source flared. The arithmetic, however, demands a lens both massive and improbably close, fine-tuned in position, of a kind that should have been detected by now and has not been. Option 2. A single fast physical event, some burst phenomenon scattering light into 3 points. But the images are clean stellar profiles at 3 distinct positions, not the geometry any known burst produces. And then there is option 3, the one that earns this entry its rank on our list. Glints. A flat, reflective surface in a high orbit around Earth will occasionally catch the sun at exactly the right angle and throw a brief flash of reflected sunlight down at the ground. To a telescope taking a long exposure, a glint from an object hovering at high altitude, moving slowly against the stars, registers as a short-lived point source, star-like, sharp, and gone by the next exposure. Astronomers today know this signature intimately because the sky now swarms with hardware, and satellite glints are a routine contaminant that survey software is specifically built to filter out. 3 glints in one small patch could mean one tumbling object flashing 3 times during the exposure, or several objects in formation catching the sun together. As an explanation of the plate, it works with almost embarrassing ease. As an explanation of the world, it detonates on contact with the calendar. The date is the 19th of July, 1952. Sputnik, the first artificial object ever placed in orbit by human beings, launched on the 4th of October, 1957. Remember the phrase from number 9, the empty sky, the fact that anchored a century of myth. Here it stops being a comfort and becomes the problem. If those 3 points are glints from reflective objects in Earth orbit, they are glints from objects that were in orbit 5 years before our species could put anything there. The authors of the paper state the possibility in exactly one careful sentence and decline to endorse it, which is what responsible scientists do when an explanation fits the data and breaks history. There is a sober alternative, and the investigators take it more seriously than the internet does. It is dirt. Photographic emulsion is a chemical surface, and chemical surfaces can be contaminated. Palomar Mountain sits roughly 200 miles from the Nevada test site, and in the early 1950s, the United States was conducting atmospheric nuclear tests there, lofting radioactive dust that weather could carry across the southwest. A radioactive particle settling onto a plate or lodging in the emulsion during handling can expose a small blob that mimics a star. It is a genuinely good hypothesis, the kind of mundane answer this video has celebrated all night, and the team has pursued it honestly, which is why the case remains interesting, because the pursuit has not closed it. Star-like images on these plates have survived the checks that defects usually fail. Under magnification, true emulsion flaws tend to betray themselves. A defect is chemistry, not optics, so it ignores the rules that govern real images. It may be too sharp, sharper than the telescope's blur allows, or shaped wrongly, or missing the faint structured halo that the instrument's optics print around every genuine point of light. A dedicated profile study of transients in the Palomar survey, published as recently as 2025, measured exactly these properties, and the uncomfortable finding was that the interesting transients look like real point sources of light, focused by the telescope, consistent with photons arriving from the sky, not like chemistry. The contamination hypothesis also has an awkward statistical wrinkle. Vanishing transients on the old plates are not sprinkled evenly through the survey's years, and one analysis noted that the summer of 1952 is unusually rich in them, which a steady rain of test site dust does not obviously explain. That same summer, as it happens, was the summer of the Great Washington, D.C. Radar and visual sightings, the most famous wave of unexplained aerial reports in American history, jets scrambled over the Capitol 2 weekends running. The plate researchers mention the coincidence in print, deadpan, as a coincidence, to be tested and not to be enjoyed, and that is the correct posture. But they did mention it, because in this business, you log everything. This case is also not an orphan, which matters for how seriously to take it. It emerged from a systematic project called VASCO, Vanishing and Appearing Sources, during a century of observations, led by Villarroel, which does exactly what its name says. It compares the digitized plate archives of the 20th century against the modern sky, hunting for sources that were solidly recorded then and are absent now. Out of roughly 600,000 old point sources examined, the project has flagged on the order of 100 candidates with no modern counterpart, and within that residue sit several more of these multiple transient events, groups of star-like points appearing and vanishing together on a single plate pair. Most of the 100 will die ordinary deaths, defects, blends, misidentifications, and the project expects that. The question is whether the residue goes to zero. The triple in Pegasus is not even the most extreme member of the collection. On a plate from April of 1950, the project's collaborators identified a field carrying not 3, but 9 star-like transients simultaneously, present in one exposure and absent from every other image of that field ever taken, before or since. Groups of vanishing points, it turns out, are a recurring signature in the early 1950s plate record, and recurrence is exactly what separates a curiosity from a phenomenon. One inexplicable plate is an anecdote. A family of them, sharing a signature and clustering in time, is a pattern demanding a mechanism, and every candidate mechanism, glints, dust, some unknown atmospheric optics, makes a different prediction about where and when the events should appear. That is what the project is now testing, plate by plate, decade by decade. The glint hypothesis, it should be said, has one more testable consequence, and it is the most cinematic experiment proposed in this entire video. If reflective objects sat in high orbits before 1957, some of them, in stable graveyard altitudes, could still be there. Villarroel and colleagues have argued in print that a targeted search of the geosynchronous belt for uncatalogued, non-functional reflective objects, combined with a hunt through the plate archives for repeating glint tracks, could confirm or kill the idea directly. Either the searches come up empty and the 1950s transients return to the chemistry of emulsions, or somewhere in the quiet high orbits above the working satellites, an inventory error of history is still catching the sun a few times a day. The experiment is cheap by astronomy's standards. Someone will eventually run it to completion, and this entry will be re-ranked by the answer. A 2026 follow-up study added a genuinely strange data point, reporting that the rate of plate transients at the geometry where geosynchronous objects glint responds to geomagnetic storm conditions, which is behavior you might expect from something physical happening near Earth, and not behavior you expect from dust in a darkroom. None of this settles anything. All of it keeps the file open. It is worth dwelling for a moment on how the human beings involved carry this case, because their conduct is a model of the posture this whole video argues for. Villarroel has been direct in interviews that the glint possibility, with everything it would imply, deserves to be tested rather than mocked, and equally direct that contamination may yet win. The team publishes its null results, invites the criticism, proposes the follow-up observations that could destroy its own most interesting interpretation, and waits for telescope time like everyone else. Nobody involved claims anything was above Palomar in 1952. They claim something narrower and harder, that a well-documented anomaly in the scientific record of the 20th century remains unexplained in the 21st, and that the explanation, whichever it is, will be worth having. Science holds files like this one open for decades without embarrassment. That patience is not a weakness of the method. It is the method. So number 5 rests exactly here. In a glass archive in California sits a photograph of 3 bright, sharp, star-like lights that existed for less than 50 minutes over the summer of 1952 and have never existed since. Either the emulsion lied in a way that has so far passed every test of its honesty, or something reflective hung above the Earth that night, in 5 years before humanity's first satellite, and the only instrument that noticed was a telescope performing a routine survey of Pegasus. Both answers cost something. One costs our confidence in the century of photographic astronomy underneath modern science, and would send archivists back through 2,000 plates asking what else the chemistry invented. The other costs considerably more, and would send historians back through the summer of 1952 asking what else the sky contained. And with that, pause for one breath, because the countdown has just crossed its border. Look at the ground we have covered. Number 10 was solved, an artificial object unmasked as our own returning rocket. Number 9 was solved, a myth dismantled into blankets and blindness. Numbers 8 and 7 were retired, honest artificial hypotheses about Phobos and 1991 VG, put down by better data, each leaving behind a natural puzzle that still stands. Numbers 6 and 5 are different. Nothing about them is solved. The echoes are real and ownerless. The plates are real and unanswered. From this point to number 1, that is the only kind of case left. Everything above this line is an open file, currently under investigation, with the word artificial still legally alive inside it. And the next entry opens the file that is largest of all in sheer scale, because it does not concern one object in one photograph. It began as a question asked of 5 million stars at once, and it ended with 7 of them that could not answer it. Number 4, 7 stars that shine wrong. In 1960, the same year Ronald Bracewell was imagining patient probes, the physicist Freeman Dyson published a 2-page paper in the journal Science with a title that sounds like administrative paperwork and contents that rewired the search for other minds. The title was Search for Artificial Stellar Sources of Infrared Radiation. The argument inside was thermodynamic, which is to say, inescapable. Any civilization, whatever its biology, chemistry, politics, or intentions, runs on energy, and the largest energy source in any planetary system is its star, pouring out more power every second than a planetary surface can intercept in years. A civilization that grows long enough, Dyson reasoned, will eventually want more of that output than its home planet's little disk can catch, and the engineering answer is to build collectors in orbit, more and more of them, until the star is partially or wholly enclosed in a cloud of harvesting machinery. And here is the beautiful, terrible catch that made the paper immortal. Physics does not allow the energy to disappear. Every joule the machinery absorbs must eventually be re-radiated as waste heat, and waste heat glows in the infrared. A star wrapped in industry would therefore dim strangely in visible light and blaze anomalously in the infrared, a fingerprint written not in any language, but in the laws of thermodynamics themselves, unfakeable and unhideable. You cannot run a civilization without warming the sky. Dyson's conclusion was a search instruction. Look for stars that shine wrong. One clarification he issued almost immediately, because the popular imagination ran ahead of him. The structure that came to be called a Dyson sphere is not a solid shell, like an egg around a star. A rigid shell is mechanically absurd, unstable against the slightest drift, and Dyson never proposed one. What he described is better called a swarm, thousands upon millions of independent collectors on their own orbits, built generation by generation, the way a coral reef is built, no single piece remarkable, the total eventually devouring a measurable fraction of the starlight. That distinction matters for the search, because a swarm can be partial. A civilization halfway through the project would produce a star that has lost, say, a tenth of its light to interception, with that tenth reappearing as warm infrared. Precisely the kind of subtle wrongness a survey might catch. Before dismissing the whole premise as science fiction wearing a lab coat, it is worth sitting with the construction problem for a moment, because the numbers are stranger than intuition expects, in the permissive direction. Enclosing a star sounds like a project beyond any conceivable civilization, and as a single monument it would be. But nobody would build it as a monument. The studied route is incremental and self-funding. Each collector built increases the energy available to build the next, and if any part of the industry is automated and self-replicating, the growth is exponential, doubling on the time scale it takes machines to copy themselves. Analyses of this arithmetic have reached a conclusion that deserves to be more famous than it is. Given automation, the disassembly of a small planet for raw material and the deployment of a star-girdling swarm could in principle be accomplished in centuries, not millions of years. Centuries are nothing. Stars live for billions of years, and the galaxy is 3 times older than our Sun. If even one civilization in the galaxy's history crossed the automation threshold and wanted the power, the product could be out there, orbiting quietly, arbitrarily ancient, its builders present, or transformed, or long gone with the machinery still faithfully soaking up the light. That is why the infrared search is not a whimsy. The fingerprint outlives the finger. For decades, the instruction sat waiting for instruments worthy of it. The first serious attempt came when the astronomer Richard Carrigan at Fermilab combed the catalogue of IRIS, the pioneering infrared sky survey satellite of the 1980s, checking roughly 250,000 infrared sources for Dyson signatures. He found dust, dying stars wrapped in their own shed atmospheres, young stars in their birth cocoons, the infrared universe's ordinary population, and nothing that demanded engineering. A null result, but also a proof of concept. The fingerprint was searchable. What was needed was a bigger net and a finer mesh, and above all, distances. Carrigan's era had infrared brightnesses, but only rough distances for most sources, and without a reliable distance, a survey cannot tell a modest nearby star with a strange warm glow from a monstrous faraway one behind a veil of dust. The two read identically in a catalogue and mean entirely different things. Infrared astronomy spent 2 decades quietly assembling the missing ingredient, and when it arrived as the most precise map of stellar positions ever constructed. The bigger net arrived in the 2020s, and its name is Project Hephaestos, a research effort based at Uppsala University in Sweden, named for the smith of the Greek gods, the builder at his forge. In May of 2024, Matthias Suazo and his colleagues published the project's second and most ambitious installment in the monthly notices of the Royal Astronomical Society. And the method deserves to be walked through slowly, because the method is the point of this entry. They began with the star map of the Gaia Space Observatory, the European mission that has measured the positions and distances of nearly 2 billion stars, and crossed it with two infrared atlases, the 2-micron All-Sky Survey and the WISE mission's mid-infrared map of the entire sky. The cross-match gave them about 5 million stars, for which both the visible light and the infrared glow were reliably measured, each with a known distance. 5 million individual candidates for the oldest question there is. Then came the pipeline, and the pipeline is where the discipline lives. A star can carry excess infrared for many innocent reasons, and the software was built to hunt them down one by one and discard. Young stars still swaddled in the dust of their own formation glow infrared, so out went every star with the signatures of youth. Stars with debris disks, the ground-up rubble of comets and asteroids like our own zodiacal dust writ large, glow infrared, so out went every candidate whose excess fit the well-studied profiles of such disks. Chance alignments, where a distant, dusty galaxy or a reddened background star sits behind the target and pollutes its photometry, mimic excess, so out went every star whose images showed blending, confusion, or suspicious neighbors. Instrumental artifacts, diffraction spikes, saturated pixels, catalog errors, each got a dedicated filter. The pipeline was, in effect, a machine for destroying its own candidates, built by people who understood that in this business, the discovery you want most is the one you must try hardest to kill. 5 million stars went in. The filters ground them down through stage after stage. And when the machinery stopped, 7 remained. 7 stars out of 5 million that shine wrong and resist every natural excuse the pipeline knew how to apply. The 7 share a profile, and the profile is odd. All are M dwarfs, the small, cool, long-lived red stars that make up most of the galaxy's population, all within roughly 1,000 light-years of Earth. Each shows a mid-infrared excess far above what its ordinary starlight can explain, and if you insist on modeling that excess as waste heat from orbiting machinery, the numbers come out coherent, with covering fractions on the order of 1/10 of the star's light, radiating at the few hundred-degree temperatures engineering would plausibly run at. The authors, to their lasting credit, said exactly what scientists should say, and no more. They did not announce megastructures. They announced 7 objects whose infrared behavior is not currently well explained, noted that a Dyson swarm interpretation is compatible with the data, and stated plainly that mundane explanations must be exhausted first, inviting the community to try. There is a strange poetry in the result, even as a placeholder. If you had asked, before the search, where engineering would most sensibly happen, some theorists would have pointed at exactly this kind of star. M dwarfs are the galaxy's economy accommodation, dim enough that a swarm needs less material, stable for hundreds of billions of years, the longest-lived real estate in the universe. The 7 candidates sit where the arithmetic of patience says builders ought to sit. Which proves nothing, and reads oddly, and everyone involved knows both things. The community accepted the invitation to attack, immediately, and this is where the entry becomes a portrait of science, working in real time. Within weeks, a team including Tongtian Ren and Michael Garrett of the Jodrell Bank Center for Astrophysics, with the SETI researcher Andrew Simeon, pointed out something the pipeline could not easily have known. 3 of the 7 candidates, labeled A, B, and G, sit suspiciously close on the sky to faint radio sources. To understand the objection, you need one technical detail, worth 20 seconds. The WISE satellite mapped the sky in 4 infrared colors, and the 2 longest wavelengths, called W3 and W4, are exactly where a Dyson swarm's warm waste heat would glow, and exactly where WISE's vision is bluntest. At those wavelengths, the telescope's images blur each source across a patch of sky several arcseconds wide, and its sensitivity is poor enough that only strong emitters register at all. The candidate signal, in other words, lives entirely in the fuzziest, most easily contaminated bins of the whole dataset, where a pinpoint of infrared from something in the background gets smeared indistinguishably onto a foreground star's account. That is not a flaw anyone hid. It is simply where the physics forced the search to look. And it opened the door to a rare and treacherous class of object called hot dust-obscured galaxies, hot DOGs in the literature's own irresistible abbreviation. These are distant galaxies in a violent phase, their central black holes feeding furiously behind shrouds of dust, and the shrouds re-radiate the violence as a torrent of exactly the mid-infrared light the Dyson search keys on. They are rare, a few in every patch of sky the size of a full moon, but WISE's infrared measurements blur across several arcseconds, wide enough that a hot DOG lurking behind a foreground red dwarf smears its glow onto the star's ledger. Run the arithmetic of chance alignment across 5 million stars, the critics showed, and the expected number of such photobombed candidates is comfortably enough to account for all 7. Not proof that all 7 are contaminated. Proof that contamination alone could explain the survivors, which converts the candidate list from a set of possible discoveries into a set of stars owed an individual audit. The audits began. In 2025, radio astronomers took candidate G into the interferometers, the networks of linked radio telescopes that synthesize a single instrument the size of a continent. The E. Merlin array across Britain and the European Velby network resolved the radio source lying beside the star, measured its position to a fraction of an arcsecond, and read its nature from its brightness. The verdict was unambiguous. The source, catalogued as J2335-0004, sits well offset from the star itself, and its brightness temperature, the intensity of its emission concentrated in a tiny region, is far beyond anything a star or its environment can produce. It is an active galactic nucleus, a feeding supermassive black hole in a galaxy far in the background, shining through coincidence within a few arcseconds of a nearby red dwarf. Candidate G's infrared excess is, at minimum, badly polluted by it, and G is effectively retired. The hot DOG hypothesis had named its first confirmed victim, and in doing so demonstrated something subtle and reassuring about the whole enterprise. The refutation machinery is sharper than the discovery machinery. Finding the 7 took a pipeline-crunching survey photometry. Retiring one of them took continent-spanning interferometry resolving positions a survey could never see. Every rung upward in the audit, the instruments get better, the scrutiny gets harder, and a candidate that survives it all will have earned a level of certainty survey astronomy alone could never grant. So the ledger of number 4 currently reads like this. 7 candidates announced. A population argument saying background galaxies could explain everything. 1 candidate individually convicted of contamination, with 2 more, A and B, carrying the same suspicious radio companions and awaiting their own audits. And a residue, the remaining candidates, that has not been individually explained by anyone because a population argument is a statement about the group, not a verdict on any single star. The decisive instrument exists and is flying. The James Webb Space Telescope's mid-infrared spectrographs can do what no survey photometry can: split the light of each candidate finely enough to tell whether the excess carries the spectral shape of a background galaxy's dust or of something warm orbiting the star itself, and proposals to point Webb at the survivors have been submitted through the standard queues. Within a few years, the list of 7 will likely be 0, or it will not be, and either outcome will be among the quietest important numbers in the history of the search. What Webb actually measures is worth spelling out, because the test is elegant. A background galaxy's dust and a warm orbiting swarm both glow in the mid-infrared, but they do not glow identically. The galaxy's emission carries the spectral signatures of its distance, features shifted by the expansion of the universe, the chemical fingerprints of interstellar grains, and it sits at a fixed point on the sky, offset from the star. A true circumstellar excess shares the star's exact position, moves with the star's own motion across the years, and carries a smooth thermal shape at a temperature the orbit dictates. Webb can read all of it in a single sitting per target. The experiment is, by the standards of the questions it touches, almost absurdly modest, a few hours of telescope time per star to adjudicate the oldest question our species knows how to ask about the night sky. There is a human note in all this that the coordinates and catalog numbers hide. Somewhere within 1,000 light-years of your bed, 7 small red suns are going about their unremarkable lives, fusing hydrogen at their patient dwarf star pace, and for the past few years they have been, without knowing it, defendants. Their light is being audited by instruments on 2 continents and in space. Their names in the papers are single letters, A through G, like parties in a sealed lawsuit. Each will eventually be acquitted, revealed as a victim of galactic photobombing or some subtler contaminant, and forgotten by everyone but the pipeline that once flagged them, or else one of them will refuse acquittal, and its letter will become the most famous name in the history of science. The stars, of course, are indifferent. The indifference is not mutual, and the asymmetry of that arrangement, small, cool suns unaware of the weight assigned to them, is one of the stranger textures of the modern search. It is worth being honest about which outcome the smart money favors, and equally honest about what the search bought regardless. The smart money says 0. It usually does, and it is usually right. But step back from the individual stars and look at what now exists. For the first time, humanity has demonstrated an industrial-scale audit of the galaxy for engineering. 5 million stars checked against a fingerprint derived from thermodynamics, with a working pipeline, a hostile review process that functions, and a follow-up pathway to a space telescope. Dyson's 2-page instruction from 1960 is now a repeatable procedure, and a complementary survey called GHAT has already run the same logic at a grander scale, checking roughly 100,000 entire galaxies with WISE for the waste heat of civilizations operating across galactic scales, and finding none above modest thresholds. Silence at that scale is itself a scientific result, with its own uncomfortable weight, because a civilization harvesting an entire galaxy's starlight is the loudest thing thermodynamics permits to exist, and 100,000 galaxies decline to be loud. Either the galaxy-scale builders are absent from our whole corner of the universe, or the growth every technological species seems pointed toward simply does not continue to those scales, for reasons every technological species presumably discovers. Both readings are information. Neither is restful. The audit exists. It will be rerun with every better instrument, on bigger catalogues, for as long as the question stays open, and the question, as of tonight, with candidates still unexplained on the table, remains open. That is the precise sense in which 7 faint red stars belong on a list of objects scientists think could be artificial. Nobody involved believes it exactly. Belief is not the currency. The candidates are unexplained. The explanation that would close them is being actively purchased with telescope time, and until the receipts come in, the word artificial sits in the file, printed in a refereed journal, entirely legally. The next entry needed no pipeline, no cross-match, and no 5 million stars. It found us, in a sense, on its own. It is a single star, 4 times brighter in fame than anything in the Hephaistos list, and it announced its candidacy in the most theatrical way a star possibly can. It switched off 1/5 of its own light, in front of the one telescope in history that was watching closely enough to see it. Number 3. The star that made astronomers say megastructure out loud. 1,470 light-years from here, in the constellation Cygnus, the swan that flies down the spine of the summer Milky Way, there is a star known to the catalogues as KIC 8462852. It is, by every classical measure, an unremarkable star, hotter than our Sun, half again as massive, a touch bigger, middle-aged, spinning at an ordinary pace, unaccompanied by anything visible and strange. If you pointed a good telescope at it tonight, you would see a faint, steady point among thousands, and nothing about it would hold your eye. For 4 years, though, this star happened to live inside the stare of the most patient eye humanity has ever built. And what that eye recorded turned an anonymous entry in a catalogue into the most argued-about star of the 21st century. The eye was the Kepler Space Telescope. From 2009 to 2013, Kepler pointed at a single patch of sky on the Cygnus-Lyra border and did one thing with monastic focus. It measured the brightness of about 150,000 stars every 30 minutes without blinking for years. The purpose was planets. When a planet crosses the face of its star, the star's light dims by a whisper, and Kepler's photometry was exquisite enough to catch whispers. A Jupiter crossing a sun-like star steals about 1% of the light. An Earth steals about 1 part in 10,000. Kepler's software combed its 150,000 light curves for exactly those signatures, tiny dips that repeat on a fixed period with a clean, symmetric shape, and it found them by the thousand, which is how our galaxy went from having a handful of known planets to a census in a single decade. The software never flagged KIC 8462852, and the reason is the whole story. The software was looking for small, neat, and periodic. This star's behavior was enormous, ragged, and lawless, so far outside the template that the pipeline had no category for it. But Kepler's data had a second audience. A citizen science project called Planet Hunters put the raw light curves on the internet and invited anyone, anywhere, to scroll through them by eye, on the theory that human pattern recognition catches what templates miss. Retirees, students, night shift workers, people at kitchen tables on several continents page through the brightness histories of anonymous stars as a hobby. And beginning in 2011, the volunteers examining this particular light curve started leaving flags on it, with comments that said, in the plain language of non-professionals, bizarre. Giant transit. What is this? The flags accumulated. The volunteers compared notes in the forums and kept returning to the same star, insisting to one another that something was deeply wrong with it, until a postdoctoral astronomer at Yale named Tabitha Boyajian took charge of the case. Pause on the sociology, because it is easy to hear citizen science as a feel-good garnish, and here it was the entire discovery. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. It was specialized, tuned to extract the faint periodic signatures of planets from noise, and specialization is blindness by design. A template search cannot find what no one thought to template. The Planet Hunters project existed precisely because its founders suspected the data contained categories of event nobody had imagined, and the human visual system, which evolution spent millions of years tuning to, notice that something is off, is still the best general anomaly detector ever pointed at a light curve. It took no degree to see that this star was wrong. It took eyes, patience, and the willingness to flag the same object again and again, while the professional world got around to listening. The volunteers did the flagging for years. Boyajian's decisive contribution began with taking them seriously. What the light curve showed, once assembled, deserves slow description. For long stretches, months and years, the star shines steadily, flat as a ruled line. Then, without warning or pattern, the light collapses. In March of 2011, the star dimmed by 15% over a matter of days, in a single deep asymmetric plunge, ragged on one side, and then recovered as if nothing had happened. In February of 2013, it went again, worse, a chaotic cluster of dips crowding one after another for weeks, the deepest of them swallowing 22% of the star's light. Hold those numbers against the scale we established. The largest planet possible blocks about 1%. Whatever crossed this star blocked 22, which requires an occulting object, or fleet of objects, of preposterous size, and the dips did not repeat on any period, did not share a common shape, and did not resemble each other from event to event. A star cannot do this to itself. A star of this type has no mechanism for flickering a fifth of its output on a timescale of days. Something outside the star, enormous and irregular and orbiting, was passing between it and us. Boyajian gathered every explanation the community could muster into a 2016 paper whose title made her colleagues smile and stuck to the star forever. The paper is formally about KIC 8462852, but its running title was a question, "Where's the flux?" and the star has been Tabby's star ever since. The paper worked through the natural suspects with care. Instrumental error was excluded. The dips are real and confirmed in independent processing. A catastrophic planetary collision, grinding worlds into a light-blocking debris cloud, would flood the system with warm dust glowing in the infrared, and infrared surveys of the star showed no such glow. Clouds of material inside a young star's birth disk would also glow, and this star is demonstrably not young. The least bad natural candidate was a swarm of giant comets, a family of icy bodies on a wild elliptical orbit, shedding dust in clumps, and even that required a comet swarm of a scale never observed anywhere. Every natural explanation survived only by being stretched. To give the comet swarm its due numbers, modeling of the deepest Kepler event suggested that explaining it with comets required something like hundreds of thousands of them, each tens of kilometers across, marshaled into clumps and delivered across the star's face on cue. Our own solar system's most famous comet, Halley, is about 11 kilometers long. The model asked for a procession of hundreds of thousands of Halleys and larger, all recent, all coordinated by orbital happenstance. It was not impossible. Nothing in the paper was impossible. It was merely the least outrageous offer on a table where every offer was outrageous, and that table is precisely where a disciplined mind starts glancing at hypotheses it would normally never touch. Into that vacuum stepped a thought that had been waiting since 1960. Jason Wright, an astronomer at Penn State who studies, among other things, exactly the waste heat searches we met at number 4, was shown the light curve, and he noticed what any Dyson-literate astronomer would notice. Enormous, irregular, aperiodic occultations by structures of arbitrary shape and size are precisely what a swarm of artificial collectors under construction would produce. Panels and habitats and half-built arrays do not cross a star the way planets do, in neat periodic winks. They cross it raggedly, in fleets, exactly like this. Wright said so, carefully, in the refereed literature and in interviews, always wrapped in the discipline the subject demands, that aliens are the hypothesis of last resort, to be reached only when everything natural has failed, but that this star was, at minimum, an outstanding target for exactly that test. In October of 2015, the word megastructure met the internet, and the internet did what it does. For a season, Tabby's star was the most famous object in the sky, the alien megastructure star of 1,000 headlines, and radio telescopes were being pointed at it in earnest. The SETI Institute's Allen Telescope Array spent weeks listening across wide bands for any leakage of transmission from the system and heard nothing, which excluded only strong transmitters aimed helpfully our way, and the silence subtracted nothing from the mystery of the light curve itself. The searches did not stop at radio. Optical SETI instruments, built to catch the nanosecond flashes a laser communication system would spray across space, examined the star as well and found the same nothing. Each null result was published, each with its stated limits, and the file grew thicker with carefully measured absence, which is how this field does its accounting. Nobody was finding aliens at Tabby's star. Nobody could yet explain the star either, and both facts were true at once for 2 full years, an interval worth remembering whenever someone tells you science cannot hold an open question calmly. Then the mystery grew a second dimension. Bradley Schaefer, an astronomer at Louisiana State with a specialty in wringing science out of historical records, went to the Harvard Plate Archive, the century-deep photographic memory of the sky we met in principle at number 5, and measured this star on plates spanning 1890 to 1989. His finding, across that century, the star faded by roughly 14%, slowly and steadily. Other researchers immediately contested the claim on calibration grounds, arguing that the Plate Archive's sensitivity drifted across the decades in ways that can manufacture false fades, and that comparison stars showed similar trends. Schaefer answered with his own checks and stood by the measurement. The dispute over the old plates remains genuinely unsettled to this day, which is its own small lesson from number 5 revisited, that a century of glass is a treasure and a minefield in the same archive. But then the same signature appeared somewhere unimpeachable. Ben Monte and Joshua Simon went back into Kepler's own 4 years of data, not the dips this time but the quiet baseline between them, and found the star fading there too, about 3% across the mission, including one interval where it slid noticeably in a matter of months. Short, chaotic dips, and underneath them, a slow, secular dimming on timescales from months to a century. No known stellar process produced either. Together they were baffling squared. Here the story turns, and it turns on money, which makes it rare and worth telling straight. To catch the star in the act, astronomers needed something unglamorous, continuous monitoring by ground telescopes, night after night, indefinitely, so that the moment a new dip began, spectrographs could be pointed at it while it was in progress. Continuous monitoring of one weird star is exactly the kind of program that funding committees decline. So Boyajian took the case to the public that had discovered it in the first place. She ran a Kickstarter. More than 1,700 people, most of them with no connection to astronomy beyond caring, pledged over $100,000 to buy a year of dedicated time on the Las Cumbres Observatory, a global network of robotic telescopes distributed around the planet so that Cygnus never sets on all of them at once. The backers voted on names for the dips they were paying to catch. Think about the shape of that for a moment. The star was flagged by volunteers, championed by a scientist willing to stake her name on an anomaly, and its decisive test was paid for directly by the curious public, 1,700 strangers buying photons. Whatever the sky turned out to contain, That arrangement says something warm about what our species does when it genuinely wants an answer. In May of 2017, the star obliged. Picture the night it began. A robotic telescope in the Canary Islands, working through its automated queue in the small hours, measures the star and finds it a fraction of a percent low. Software compares, hesitates, confirms, and sends the alert. It is evening in Louisiana when Boyajian's phone sounds, and within hours the network is awake. Observatories in Hawaii, in California, in the Canaries, handing the star westward around the planet as the Earth turns, so that someone is always watching it fall. For the first time in the history of this mystery, humanity watches a dip happen live, the light curve sagging on screens on 3 continents, in something close to real time, 2% down, recovering, and everyone with a spectrograph in reach drops what they are doing and swings towards Cygnus. The backers' chosen names went on to the events as they came that summer. Elsie, Celeste, Skara Brae, Angkor, 4 dips caught in the act by the instrument the public bought. And the light, measured properly at last, gave up the answer it had been withholding for 6 years. The dips were deeper in blue light than in red. Sit with that sentence, because it is the entire resolution. A solid object, a panel, a shell, a machine, a megastructure, is opaque. It blocks blue and red light equally, indifferently, like a hand in front of a lamp. Fine dust does not. Small grains scatter short blue wavelengths more efficiently than long red ones, so starlight, filtered through a veil of dust, arrives reddened, and the thinner the grains, the stronger the effect. The 2017 dips were emphatically color-dependent. Whatever crossed the star that summer was not opaque hardware. It was dust, in clouds and streams, ordinary in substance if not in arrangement. Parallel work sealed the larger picture, with NASA's Spitzer and Swift telescopes finding that the long-term dimming also behaved chromatically, consistent with a veil of circumstellar dust, grains large enough to resist being blown away instantly, small enough to redden. By 2018, the megastructure was dead, killed not by ridicule, but by photometry, and Boyajian's team wrote the epitaph in exactly those terms. This is likely dust. One more piece of the system deserves its sentence before we open what remains. Tabby's star is not entirely alone out there. Careful imaging and the Gaia mission's distance measurements have established that it has a small companion, a dim red dwarf, orbiting at an enormous separation, hundreds of times the distance from the Sun to the Earth. At that range, the little star takes on the order of 10,000 years to complete an orbit, far too slow and far too distant to be crossing anything or blocking anything on human timescales. But wide companions are not innocent bystanders over deep time. Their slow gravitational influence can stir the outer icy reaches of a planetary system, tipping comets inward over millions of years, and if the dust veiling Tabby's star is the wreckage of infalling icy bodies, the quiet red dwarf in the distance is a suspect for who has been doing the tipping. It is the kind of detail that changes nothing this decade and might explain everything on the timescales the star actually lives by. But do not let the tidiness fool you, because number 3 remains an open file, and here is what is still inside it. Dust is a material, not an explanation. Radiation pressure from an F-type star clears fine dust from close orbits on timescales of months to years, so the veil must be actively replenished by something, an ongoing process of destruction operating in that system right now. What is being destroyed, and by what, remains unknown. Published candidates include a shredded family of giant exocomets still grinding themselves to powder, and a scenario with a genuinely uncomfortable texture that the star is consuming, or has recently consumed, one of its own planets or moons, with the debris of the meal still raining and smearing through orbit, a hypothesis whose informal name, the plunet, does not soften what it describes. The century scale fading, if the historical plates are right, wants an explanation on a time scale none of these mechanisms comfortably supplies. And the star has kept performing. After the crowd-funded campaign ended, the dips continued. New events in 2019 and beyond, tracked now by a standing patrol in which amateur astronomers with backyard equipment contribute measurements alongside the professional networks, because a bright, misbehaving star is one of the few frontiers where a dedicated hobbyist's data still matters to the literature. Each new dip gets a color measurement, and each has come back consistent with dust, the acquittal re-earned event by event. The star still dips on its own schedule, and the watch continues every clear night, because the file is still open. A handful of stars with faintly similar behavior have been found since, suggesting a rare natural class rather than a singular event, which is comforting, and the class as a whole has no accepted mechanism either, which is not. Boyajian, for her part, has said that the answer she got was better than the one the headlines wanted, and it is easy to believe her. A megastructure would have been an ending. Dust from an unknown ongoing catastrophe is a beginning, a real astrophysical process operating today in a system we can watch indefinitely, with a mechanism still to be won. She now runs a research group. The volunteers who flagged the star are thanked by name in the literature, and the dips that made a career and a controversy continue arriving from Cygnus at the speed of light, 1470 years old on delivery. So Tabby's star ends tonight as the warmest entry on this list and one of its most instructive. An anonymous star, flagged by amateurs, defended by a scientist who refused to drop an anomaly, accused in respectable journals of wearing machinery, tested by telescopes the public bought, and acquitted by the color of its own light, leaving behind a genuine unsolved mystery of the ordinary kind, which is to say the kind that is merely about the universe rather than about neighbors. The acquittal held because the object could be watched. The star sits there, 1470 light-years away, dipping whenever it pleases, available for as many years of scrutiny as the question requires. The next object on this list extended no such courtesy. It crossed our sky exactly once, moving too fast to belong to the sun, and as it left, with the whole of modern astronomy scrambling after it, it did the one thing nothing natural was ever seen to do before. Without any visible reason, it sped up. Number 2. The visitor that accelerated. On the 19th of October 2017, an astronomer named Robert Werrick was reviewing the night's harvest from the Pan-STARRS 1 telescope on Haleakala, the same instrument that would later catch our returning Centaur stage at number 10, when he found an object moving wrongly. Not slightly wrongly, fundamentally wrongly. Every asteroid and comet humanity had ever catalogued, hundreds of thousands of objects across 2 centuries of record-keeping, moves in a closed curve around the sun, an ellipse, the shape of belonging. You can stretch an ellipse enormously, fling an object out beyond Pluto for thousands of years, and it remains an ellipse, and the object remains ours, bound to return. The path Werrick was looking at did not close. It was a hyperbola, an open curve, the trajectory of an object moving too fast for the sun's gravity to ever reclaim it. Whatever this was, it had fallen in from interstellar space, was swinging once through our solar system, and would leave forever. Follow-up measurements over the next nights hardened the conclusion past all doubt. Its eccentricity, the number that measures how far a path departs from a circle, came out near 1.2, unambiguously beyond the boundary of bound orbits, and its speed far from the Sun was about 26 kilometers per second, an excess velocity no slingshot within the solar system could have manufactured. After 2 centuries of watching gravel that belongs to us, humanity had caught its first confirmed visitor from somewhere else. The naming committee reached for Hawaiian, honoring the observatory that found it, and chose a word that means something close to a messenger from afar, arriving first, a scout. It received the formal designation 1I, the first interstellar object, and the name Oumuamua, chosen in consultation with Hawaiian language and culture experts, a small act of care that gave the first confirmed emissary from another star a name from the islands whose mountain caught it. And it is worth appreciating how narrow the catch was. The object is small, a few hundred meters, and dark, and it was detectable at all only because it happened to pass within about 60 times the distance of the Moon. Pan-STARRS caught it at the very edge of its capability, weeks after its closest approach to the Sun. Had it threaded the solar system a modest distance farther out, or arrived 2 decades earlier, before survey telescopes of this class existed, it would have come and gone entirely unrecorded, and statistical arguments suggest that this is precisely what such objects have been doing throughout human history, sliding through the solar system unseen at a steady traffic rate, perhaps one within the orbit of Earth at any given moment. We did not start being visited in 2017. We started noticing, and almost everything about the visit conspired toward frustration. The object had actually made its closest pass by the Sun in early September, weeks before discovery, and was found already outbound, receding, fading. The window for studying the first known object from another star system was not going to be years or months. It was weeks, and the world's major telescopes dropped their schedules and spent those weeks staring. What they measured has not stopped bothering people since. Start with the shape. Oumuamua's brightness rose and fell by a factor of about 10 every 7 to 8 hours. Every small body tumbles and varies as it shows different faces to the Sun, but a factor of 10 was beyond anything in the catalogues, and the geometry it implies is extreme. The object had to be at least 6 times longer than it was wide, perhaps 10 times, a few hundred meters in its longest dimension, shaped either like a cigar or in later reanalyses that fit the light curve slightly better, like a flattened plate. A pancake. Nothing round about it, in a universe whose gravity prefers to build round things. And its spin was not the clean rotation of a settled body. It was tumbling, turning about multiple axes at once, in the way of an object that suffered violence somewhere in its past, and has been left in a slow, chaotic cartwheel that, in the vacuum, can persist for longer than the age of the solar system. The tumble is a fossil of an event, an ejection collision in its birth system, a tidal shredding by a star or giant planet, some catastrophe old beyond dating, carried across the galaxy in the spin state, the way scars carry a memory of the wound. Its color was the deep red of surfaces cooked for eons by cosmic radiation, familiar from the oldest bodies of our own outer system. Its origin direction, traced backward, pointed roughly toward the bright star Vega in the constellation Lyra, though it had drifted so long that Vega was not there when it left. More telling was its speed relative to the neighborhood before arrival, which sat close to what astronomers call the local standard of rest, the average drift of the galactic traffic in our region. That is the velocity of something that has been coasting between the stars for a very long time, long enough to be averaged into the flow, plausibly hundreds of millions of years, plausibly more. An old, red, battered shard from an unknown system, taking one pass through ours. Astronomers naturally tried to trace it home. A careful study using the Gaia catalogue ran the trajectory backward through the gravitational field of the galaxy and identified a handful of candidate dwarf stars whose positions and motions millions of years ago put them plausibly near the object's path. None is a confident match. The honest answer to where it came from is a shrug spread across 100 million years of drift, because an object coasting between stars for that long passes near many, and its birthplace dissolves into statistics. It carries no return address. It only carries the where of the journey. Then came the two absences, and the two absences are the heart of the case. First, no coma. A comet nearing the sun grows its signature veil, gas and dust boiling off the warming ice, visible as a fuzz and a tail even for modest specimens. Oumuamua, at its closest, passed well inside the orbit of Mercury, receiving heat that would set any ordinary icy body venting furiously, and the deepest images from the largest telescopes showed nothing. No fuzz, no tail, no dust, to stringent limits. Afterward, the Spitzer Space Telescope hunted for the infrared glow of carbon-based gases around it and found nothing at all, setting hard ceilings on ordinary cometary activity. So, the community concluded, it must be an asteroid, a dry rock, and dry rocks obey gravity to exquisite precision. That teed up the second absence, which is really a presence. In June of 2018, a team led by Marco Micheli of the European Space Agency and Karen Meach of the University of Hawaii published, in Nature, the combined analysis of every measurement of Oumuamua's position, from the world's telescopes and from Hubble, which had tracked it farther out than anything else could. The trajectory did not fit gravity alone. Something was pushing the object, gently and continuously, away from the sun, and the push declined with distance following an inverse square, the exact mathematical signature of sunlight and of solar heating. The detection was not marginal. It stood at roughly 30 sigma, a level of statistical certainty at which doubt about the measurement itself becomes unreasonable. The first interstellar visitor was accelerating, and it had no visible means of doing so. Comets accelerate this way. That is textbook physics, the rocket effect of gas venting from warmed ice. But a comet producing this much push produces a coma, and there was none. Worse, jets of escaping gas exert torque, and an elongated tumbling body being shoved by jets should have had its spin visibly altered over the months of observation, and the tumble stayed steady. Every standard explanation came packaged with a contradiction. It is worth lining the ledger up plainly, because no single anomaly makes this case, and the ensemble does. A shape more extreme than any of the million-plus catalogued bodies of our own system. A tumble instead of a spin. A surface with no trace of ice on an object behaving as if it were venting. An acceleration measured at a certainty level physicists reserve for their most established results, with a profile matching sunlight, on a body showing nothing for sunlight to push against in any conventional way. Any one of these alone would have earned a workshop and a few papers. All of them, together, on the first ever visitor from interstellar space, on an object available for study for only weeks, is the kind of hand the universe deals once in a career of centuries. And so, in the last months of 2018, the gap in the middle of the data received the most famous unwelcome guest in modern astronomy. Shmuel Bialy and Avi Loeb of the Harvard-Smithsonian Center for Astrophysics published a calculation in the Astrophysical Journal Letters asking a question that was, on its own terms, entirely legitimate. What would it take for sunlight alone, the sheer pressure of light we met at number 10, to produce the measured push? Their answer: the object would need to be extraordinarily thin, a sheet less than a millimeter thick spanning tens of meters, with a mass so low that photons could steer it. Nature does not manufacture millimeter-thin sheets hundreds of meters wide. Engineers have designed them for decades, and we build them ourselves. They are called solar sails, and our own species has flown several, the Japanese Ikaros craft riding sunlight to Venus in 2010, the Planetary Society's light sail tacking around Earth on photons a few years later. The sail reading even offered explanations for the other anomalies as a bundle. A thin plate tumbling explains an extreme light curve naturally. A surface without ice explains the missing coma by having nothing to vent. The proposal was internally coherent, which is exactly what made it so uncomfortable. The listening followed immediately, because whatever one thought of the sail, the test was cheap. The Breakthrough Listen project pointed the 100-meter Green Bank telescope in West Virginia at Oumuamua across multiple radio bands for hours while it was still within range. The sensitivity was extreme. A transmitter aboard the object with the power of a single cell phone would have been detected. Nothing was heard in that campaign or any other, and the silence retired the liveliest versions of the hypothesis, the functioning probe, the active machine. What silence cannot retire is wreckage. A dead sail, a shed fragment of light structure, transmits nothing, and the debate settled into the form it still holds, not aliens versus no aliens, but exotic natural ice versus derelict artifact, with both explanations orphaned by the departure of the only evidence. Loeb, the chair of Harvard's astronomy department, did not stop at the calculation, and over the following years he argued the case at book length to the widest audience any such claim has ever reached, that Oumuamua's ensemble of oddities, the shape, the shine, the silence, the push, is most economically explained as a piece of technological debris, a defunct sail or lightweight structure from another civilization, tumbling through our system the way our own Centaur stage tumbles through theirs, if anyone is there to be puzzled by it. The scientific mainstream disagreed, sharply in places, and the years since have been a contest of natural models, each trying to supply the missing engine without the missing coma. The most persuasive arrived in Nature in March of 2023 from the astrochemist Jennifer Bergner and the planetary scientist Darrell Seligman. Their mechanism is quietly elegant. During the object's long eons in interstellar space, cosmic rays penetrating its water ice would have split some of it, manufacturing molecular hydrogen and trapping it within the ice's disordered structure. As the object warmed near the sun, the ice annealed, its structure relaxing and reorganizing, and released the trapped hydrogen. Hydrogen is the lightest gas, nearly invisible to the observations that were taken, and venting it produces thrust with almost no dust, no visible coma, and far less torque than ordinary cometary jets. The numbers, they showed, fit the measured acceleration for a body of Oumuamua's size without exotic composition. Loeb disputed their thermal calculations in public, and in print they responded, and the exchange remains a live disagreement between named scientists in refereed venues, which is, whatever else one thinks, exactly where such a disagreement belongs. A word about the temperature of that whole debate, because it shaped the field. Loeb's campaign divided colleagues in a way few scientific arguments do, less over the calculation, which was straightforward, than over the confidence of the conclusion and the size of its audience. Critics argued that leading the public toward an artificial reading of ambiguous data spends science's credibility. Loeb answered that refusing to state a viable hypothesis because it is socially risky is its own corruption of method, and that anomalies deserve to be followed wherever they point. Both positions contain something true, and listeners of this video will recognize the tension, because it has run under every entry tonight, from Shklovsky's Hollow Moon to Steele's probe paper. The line between a scientist honestly naming an unlikely hypothesis and a culture eagerly assembling a black night is real, and it is thinner than either side finds comfortable. Alternative natural models remain on the table too, a shard of nearly pure nitrogen ice broken off a Pluto-like world, a body of such fantastic porosity that light itself could push it, each with its own strained statistics. And intriguingly, our own solar system has since supplied a possible bridge, a newly recognized population called dark comets, small bodies on local orbits that show measurable non-gravitational accelerations with no visible coma, hinting that quiet, nearly invisible outgassing may be a routine trick of small bodies everywhere, and that Oumuamua may simply be the interstellar member of a family we are only now learning to see. What cannot happen, ever, is the direct test, and this is the wound that keeps number 2 open. Oumuamua is gone. It crossed the orbit of Neptune years ago and recedes into the dark at a pace no existing spacecraft can match, unreachable by anything we currently build. A mission study called Project Lyra has examined, seriously, whether a probe launched in the coming decades using gravitational slingshots and a hair-raising dive close past the Sun could still chase it down decades from now, and the mathematics answers barely yes at enormous cost, and the funding answers no. The window even has a closing date of sorts, since a chase mission becomes more expensive with every year of head start the object gains, and the mathematics that says barely yes today will eventually say simply no. Unless that changes, every argument about the first visitor is an argument about archived data, a fixed and finite record that will never grow by another byte. Scientists will be reprocessing those same weeks of photometry and astrometry for decades, wringing new constraints from old photons, the way historians reread a single surviving letter. Remember the question mark from number 7, the 10-meter object that shared Earth's orbit, while a probe hypothesis waited 26 years for its return and its answer. That was the mercy of the solar system's clock. Objects that belong come back. Oumuamua is the question mark that never comes back, the first data point of an entire category, examined for a few weeks with instruments that were pointed elsewhere when it mattered most, and then withdrawn from evidence permanently. What we have instead is context, slowly accumulating. In August of 2019, an amateur astronomer in Crimea, Gennady Borisov, discovered the second interstellar visitor with a telescope he built himself, and 2I Borisov turned out to be gloriously ordinary, a textbook comet with a proper coma and tail, differing from local comets only in its address. There is a lovely symmetry in Borisov the man that this video should not skip. The first interstellar object was found by one of the most powerful survey machines on Earth, operated by institutions, examined by space telescopes. The second was found by one individual at a homemade observatory, scanning the morning sky near the Sun, where the big surveys do not look, with an instrument he ground and assembled himself. The sky still admits amateurs to its biggest moments, which, after number 3's kitchen table volunteers, makes twice in 2 entries. In 2025 came the third visitor, 3I Atlas, caught by a survey telescope in Chile, again an active comet, again recognizably normal chemistry doing recognizably normal things, studied this time by a coordinated global campaign that had learned from 2017 how not to be caught flat-footed. The sample now stands at 3, and the score is 2 ordinary comets and 1 tumbling, coma-free, accelerating plate. The first one remains the only strange one, which either means we caught a rare kind of object on the first draw, the kind of luck that statistics frowns at, or that the strangeness was never in the object. The referee for that dispute is under construction. The Vera Rubin Observatory in Chile, beginning its decade-long survey of the entire southern sky every few nights, is expected to catch interstellar visitors at the rate of 1 or more per year, and to catch them earlier, on approach, with time to study them properly, possibly with time to launch toward one. Within a decade or two, Oumuamua will sit inside a real population, and we will finally know whether it was a typical specimen seen badly and briefly, or a genuine anomaly, the one member of the sample that behaved like nothing else. There are contingency plans now that did not exist in 2017, mission concepts held at readiness, including a European Space Agency project called Comet Interceptor, a spacecraft designed to launch and then wait in space, parked and patient, for a suitable target to appear, so that the next time something extraordinary falls through the solar system, humanity has a vehicle already on the road. Either answer will be delivered too late for the object itself, which is now beyond the reach of every question. That is number 2, the strongest, purely scientific case on this list. A confirmed visitor from another star system, with a measured 30 sigma anomaly in its motion, no confirmed mechanism, a published artificial hypothesis from a Harvard chair, a leading natural explanation still contested by name in the journals, and no possibility, ever, of examining the evidence again. Only one entry can outrank a file like that, and it does so by holding the single card Oumuamua can never hold. The last object on this list did not fly past and vanish into the dark. It arrived 3 years earlier, and it came down. It ended its interstellar journey in our own atmosphere, over our own ocean, and human beings have gone to the bottom of that ocean to look for what is left of it. Number 1. The object we may have pieces of. The last object on this list is also the smallest, the fastest, and the only one that no telescope ever photographed. It announced itself just once, at 17 minutes past 10 in the morning, Universal Time, on the 8th of January 2014, as a fireball in the sky off the northeastern coast of Papua New Guinea, near Manus Island. A meteor, about half a meter across by later estimate, the size of a washing machine, came down over the Pacific at colossal speed, flared in 3 quick pulses of light as it broke apart under the deceleration, and was gone, its dust and fragments settling into the ocean. Nobody on Earth thought anything of it, because nobody knew. Events like it happen somewhere over the planet every few weeks, and this one burned over open water. It would have remained a row in a database forever, except for what the row said. The database is NASA's Fireball Catalog, maintained by the Center for Near-Earth Object Studies, the same office whose director unmasked our Centaur stage at number 10. Its entries do not come from astronomers. They come from United States government sensors, satellites and infrasound stations built and operated for national security purposes, whose exact capabilities and error characteristics are classified. Those sensors log the bright meteors of the world, and for each event, the catalog records a time, a position, an altitude, an energy, and a velocity vector, the speed and direction of arrival. For the Manus Island fireball, the recorded speed at impact was about 45 kilometers per second. And that number, if taken at face value, is a thunderclap. Work backward through the geometry of Earth's own motion and gravity, and an object hitting the atmosphere at that speed, from that direction, was traveling far too fast to be in orbit around the Sun. Before it met us, out in interplanetary space, it was moving at roughly 60 kilometers per second relative to our star, unbound, hyperbolic, passing through. The same signature that made Oumuamua historic, stamped on a rock 3 years before Oumuamua was discovered, and this rock did not fly past. It came down. The people who noticed were Amir Siraj, then an undergraduate at Harvard, and his advisor, the same Avi Loeb who has run through the last 2 entries of this list. In 2019, combing the Fireball catalog for exactly this signature, they found the Manus Island event, did the arithmetic, and wrote up the claim that this half-meter body, catalog designation CNEOS 2014-0108, since nicknamed IM-1, Interstellar Meteor 1, was the first interstellar object ever detected hitting the Earth. And then the paper hit a wall, unlike anything in normal science. The journals could not properly referee it. The whole claim balanced on one number, the velocity, and the error bars on that number belonged to classified military sensors. No reviewer could check how accurate the measurement was, because the accuracy itself was a secret. For 3 years, the paper hung in limbo, a discovery that could not be verified by the civilian world that had made it. The claim also carried a statistical implication that deserves a sentence, because it reframes the whole subject. If a half-meter interstellar rock really did strike Earth in 2014, then such strikes cannot be rare. Earth is a small target in a large shooting gallery, and catching even one impact in a decade of records implies that interstellar debris of this size is passing through the inner solar system in enormous numbers, millions of objects at any moment, almost all of them missing everything and sailing on. Oumuamua at hundreds of meters was a once-a-generation telescope catch. Washing machine-sized visitors, if IM-1 is real, are a steady, quiet rain, and the atmosphere of our planet has been a detector for them all along, logging arrivals in fire that nobody thought to read as mail from other stars. What broke the deadlock was among the strangest documents in the history of astronomy, a memorandum from the United States Space Command, released in April of 2022 over the signature of its Deputy Commander, Lieutenant General John Shaw, conveying the assessment of the Space Force's chief scientist. The memo stated that the velocity data reported to NASA for the 2014 event was sufficiently accurate to confirm an interstellar trajectory, with a stated confidence of 99.999%. Read that situation for what it was. A branch of the American military, in a public letter, vouching for the interstellar origin of a meteor, based on measurements it declined to show anyone. The astronomical community split precisely along the seam. For some, official confirmation was confirmation, and IM-1 entered the record books with a plausible claim to being the first known interstellar visitor, 3 years ahead of Oumuamua. For others, a letter is not a measurement. Meteophysicists, who spend careers cross-calibrating instruments, pointed to a documented and awkward fact. In the handful of cases where fireballs in the government catalogue were also tracked by independent scientific networks, the catalogue's velocity vectors have sometimes disagreed with the scientific ones substantially, and the errors grow at the fast end of the distribution, exactly where IM-1 lives. If the recorded speed is off by a modest fraction, the object was a fast but ordinary member of our own solar system. The community's leading fireball researchers made exactly that case in print. So the very first layer of this file, the claim that the object is interstellar at all, is contested, with a military attestation on one side and civilian error analysis on the other, and no way to open the sensors and settle it. Every layer above repeats that pattern. The second layer is strength. The fireball data, whatever its velocity errors, records the altitude at which the object broke up, and IM-1 held together unusually deep into the atmosphere for something moving that fast. The pressure needed to break it, by Loeb's team's estimate, placed it among the toughest objects in the entire fireball catalogue, sturdier than ordinary stony meteors, sturdier by their reckoning than iron ones. Skeptics answer that this inference, too, leans on the classified numbers, and that fragmentation physics is messy. But it was the strength argument, material tougher than familiar rock, married to the speed argument, that pushed Loeb toward the step that makes number 1 unique on this list, and frankly, unique in the history of the subject. Every other contested object tonight has been argued about from armchairs and observatories. This one has a crash site. The fireball's position fixes it to a strip of the Western Pacific, and whatever survived the entry, ablated droplets at minimum, possibly fragments, went into the water and onto the seabed, 2 kilometers down. Loeb decided to go and get it. The The Galileo Project expedition sailed in June of 2023 aboard a ship called Silver Star, funded privately, organized with the veteran expedition firm IOS under expedition leader Rob McCallum, whose previous logistics included some of the deepest crewed dives ever made, and crewed by a mix of professional ocean engineers and Harvard researchers. The planning problem alone was formidable. A fireball's recorded position marks where it burned, not where its remains settled, so the team had to model the fragment's fall through 100 kilometers of atmosphere and 2 kilometers of water column, drifting on winds and currents, spreading a half-meter object's residue across kilometers of seabed. The result was a search box tens of kilometers long and a plan to drag it in stripes, the way searchers mow a field. Their instrument was almost absurdly simple: a sled of magnets, a meter-scale steel frame strung with powerful magnetized blocks, winched down to the seafloor and towed slowly through the top layer of sediment, then hauled up and combed for whatever iron-loving material had stuck. Picture the deck of that ship on a recovery night, because it is the closing scene of this whole countdown, and it earns the space. It is past midnight, mid-Pacific, the nearest coast 100 kilometers of blackness away. The winch pays in cable for the better part of an hour, 2,000 meters of it, and the sled breaks the surface, streaming water under the deck lights, its runners furred with grey-brown sludge. Researchers in headlamps and gloves rinse the magnets over sieves, wash the sludge down through finer and finer mesh, and carry the residue inside to the microscope bench where the ship's roll makes the eyepiece sway gently. And there, among the black grit, a sphere rolls into the light. Perfect, sub-millimeter, molten-born, a tiny glass-metal bead formed when a droplet of something liquefied in the sky and froze in flight. To hold the tray is to hold the method of this entire video compressed into a fingertip of grit, an interstellar question hunted with a magnet, weighed in micrograms. Across 2 weeks and 26 sled runs along and around the calculated path, the expedition recovered on the order of 700 such spherules from the Pacific seabed. The runs were not all inside the target box, and that was the point. Several dragged sediment deliberately far from the calculated path, in waters the meteor could not have seeded, because the only way to claim that anything found in the box is special is to know precisely how much of the same material the ordinary seabed serves up everywhere. Background subtraction is unglamorous, and it is the difference between treasure hunting and science, and the expedition, whatever its critics would later argue about its coordinates, built the comparison into its own design. There is a bitter irony in where it fell, worth naming. Had IM-1 come down over land, over a desert or an ice sheet, meteorite hunters would have walked the strewn field within weeks, collecting walnut-sized stones with their bare hands, and this entry would read completely differently. Antarctica alone has yielded tens of thousands of meteorites to systematic searches, dark stones lying on white ice like punctuation on a page. Instead, the object chose the single hardest archive on the planet, deep tropical ocean, where a search means a ship, a winch, and a magnet, where the recoverable material is not stones but droplets, and where a century of human maritime traffic has salted the same sediment with exactly the industrial residues that make every claim contestable. The ocean preserved the evidence and contaminated the context in the same gesture. Everything difficult about number 1 flows from that geography. Spherules themselves are not exotic. Molten droplets rain out of every large meteor, and the deep ocean floor everywhere holds a background drizzle of them, accumulated over millions of years, along with spherules from volcanoes and from industry. Everything therefore depends on chemistry and on statistics against that background, which is why the expedition also dredged control samples far from the calculated path to learn what the ordinary seabed contains. The analysis, led at Harvard by Stein Jacobson, a senior and widely respected geochemist, ran through the standard machinery of modern cosmochemistry, electron microscopes reading each sphere's texture and structure, mass spectrometers dissolving micrograms of material and counting its atoms element by element, isotope ratios measured to the precision that lets a laboratory distinguish Earth from Moon, from Mars from asteroid in a fleck of dust. This is the same toolkit that authenticates lunar samples and identifies meteorites from Mars, science with decades of trust behind it, and it examined 57 spherules in the first round. Most were unremarkable, matching known meteoritic and terrestrial types, exactly as the background predicts. A minority were not. The team described a composition they labeled Belar for its defining enrichments, beryllium, lanthanum, uranium, and a suite of related heavy elements, elevated in the strangest cases up to hundreds of times the levels found in the Sun and in primitive meteorites, alongside a depletion of volatile elements consistent with a violent thermal history. The pattern, the authors reported, matched nothing in the geochemical literature, not crustal rock, not mantle, not lunar or Martian material, not known meteorite classes. Their speculation, offered as speculation, was that the droplets might sample the differentiated crust of a distant rocky world, a planet that melted and sorted its elements as Earth did, and whose fragments something later scattered into the deep. If any of that held, the vial in Jacobson's laboratory would contain the first material from beyond the solar system ever held in human hands. The counterattack came from every direction at once, and number one earns its crown precisely because of what happened next, an argument conducted at full technical depth, in public, over physical evidence, with every party publishing. The location came under fire first. The expedition had narrowed its search box partly using a seismic record from Manus Island, a ground vibration signal timed near the fireball. Benjamin Fernando, a planetary seismologist then at Johns Hopkins, led a reanalysis and concluded the signal was not the meteor at all. Its character changed direction over time, in a way that traced, in his team's words, the road that runs past the seismometer. The vibration, they argued, was a truck. If so, the sled may have combed a strip of ocean the meteor never touched, and the spherules are just the ordinary background rain. Loeb's reply, in print, was that the search box rested primarily on the Department of Defense satellite timing and position data, with the seismometer merely narrowing it, and that the recovered strange spherules clustered along the sled runs in a way background should not. The chemistry came under heavier fire. A critique led by the planetary scientist Steve Desch argued the Belar pattern was not celestial at all, but industrial, resembling the chemistry of coal ash, the residue of a century of steamships and dumping, an explanation with the advantage of invoking the best documented contaminant in the modern ocean. A separate analysis argued the spherules could be microtectites of terrestrial laterite, ordinary tropical soil launched skyward by an ancient impact, under a title with more wit than most journals allow, "What Goes Up Must Come Down." The Harvard team answered both with element-by-element rebuttals, arguing the measured abundances, including elements coal ash cannot supply in the observed ratios, and isotope systems inconsistent with young industrial material, do not fit the proposed contaminants. Further isotopic work, including searches for tracers like iron-60, the supernova fingerprint with a 2.6 million-year half-life, has been deployed to test age and origin directly. That argument is still running in laboratories and journals as you listen to this. If the shape of this fight feels familiar, it should, because planetary science has been here before, and the precedent is instructive about how such stories end. In 1996, NASA scientists announced that a meteorite from Mars, found in the Allen Hills of Antarctica and catalogued as ALH 84001, contained structures resembling fossilized microbes, possible evidence of ancient Martian life, announced from the White House itself. The claim was physical, the samples were real and shareable, and the community spent years attacking every layer of it, the shapes, the minerals, the organic traces, proposing non-biological routes to each. The consensus that eventually settled was that the evidence did not require life, and most researchers today read the structures as mineralogy, not biology. And yet nobody regards the episode as a disgrace. The fight over that one rock built modern astrobiology, forced the invention of stricter standards for biosignatures, trained a generation of instruments and scientists, and the sample sits in its archive still, available to any laboratory that thinks it can do better. Physical evidence loses arguments and keeps giving. That is the lineage IM1's spherules have joined, whatever they are. Step back then, and look at what number 1 actually is, because it is not what either camp's headlines say. It is a file contested at every single layer. The speed rests on classified sensors vouched for by a general and doubted by meteorphysicists. The crash site rests on a signal that was either a bolide or a delivery truck. The chemistry rests on droplets that are either the crust of an exoplanet or the ash of a steamship, and the sober truth is that no published analysis has yet forced either conclusion. And yet, unlike every other entry tonight, the argument is anchored to matter. 700 spheres exist. They sit in laboratories in Massachusetts, and with collaborators available for reanalysis, for better instruments, for hostile replication, which is the one gift no other mystery on this list ever gave its investigators. The Black Knight dissolved when questioned. Oumuamua left before the second question could be asked. IM1's evidence, whatever it turns out to be, stays on the bench. We have been fooled before, by ourselves, and the phrase from the bottom of this countdown comes home here with its meaning inverted. At number 10, the test of artificiality was a spectrum matching our own stainless steel, and the mystery deflated into a homecoming. At number 1, the test is chemistry again, run in the world's best laboratories, and this time the material matches nothing of ours, and nothing of anyone's, and the honest state of knowledge is that we do not know what is in the vial. Perhaps the first touched fragments of another solar system. Perhaps, for the second time tonight, our own residue, coal and steam instead of steel, the industrial age settling back onto us from the seabed. Both possibilities are humbling. Only one of them lets you sleep entirely easy about how much of the sky we have actually understood. And the file is designed to grow. The same catalog that holds IM1 holds a second candidate, another fireball with a claimed unbound velocity, IM2, from March of 2017, awaiting its own scrutiny, and the Vera Rubin Observatory's coming flood of early warning discoveries will eventually let scientists watch an interstellar object all the way from deep space to a calculable splash point and sail for it with certainty instead of controversy. Imagine that future recovery for a moment, because it is coming within many listeners' lifetimes. An object flagged on approach, months out, its unbound orbit confirmed by 100 observatories with error bars a referee can hold. Its entry filmed from aircraft, its fragmentation tracked by radar, its splash zone computed to a box a few kilometers wide, with ships already steaming toward it. Fragments on the bench within a month, their interstellar identity beyond dispute, and every instrument that has spent this decade arguing over the Manus Island droplets already calibrated and waiting. When that day comes, the 2023 expedition will be remembered as the rough draft, the voyage that worked out, in public and under fire, how humanity goes to sea to collect another star system's mail. The first attempt will be remembered either as the expedition that touched another star system with a magnet, or as the most instructive wrong turn in the modern search, and both futures are worth having on the record. So the countdown ends in a drawer in Massachusetts, and it is worth assembling the whole list one last time before we put it away. 10 objects, and the word artificial survived contact with exactly none of them in the way the headlines hoped, and yet the question came back stronger every time it was tested. A rocket stage we mistook for a mystery, and a myth we built from blankets and longing taught us the method. A hollow moon and a patient question mark in Earth's orbit taught us that honest arithmetic can be wrong and still be honorable. A century of echoes and 3 vanished lights on glass taught us that some records simply refuse to close. 7 red stars, a dipping giant in Cygnus, and a visitor that sped up taught us that the orbit is now permanent, industrial, and unfinished. And a fireball over the Pacific taught us that the question has finally become physical, something a ship can sail toward and a magnet can touch. Nothing on this list proves anyone is out there. Everything on this list proves we have learned how to ask properly, and that the sky keeps answering with just enough silence and just enough strangeness to keep the file open. The search will go on tonight without you. Telescopes are watching Tabby's star, software is sifting 5 million infrared ledgers, and somewhere a spherule is waiting its turn under a microscope, and none of it needs you awake. The universe has kept its secrets for 13 billion years. It will still have them in the morning. Sleep well and good night.